take a deep breath. The universe is vast, and tonight we are exploring it together. There is a concept in theoretical physics that challenges everything we think we know about existence itself. It suggests that the universe you inhabit, the one containing every star you've ever seen, every atom in your body, every moment you've ever experienced, may be just one among an infinite collection of universes. Not metaphorically infinite, mathematically infinite. Tonight we will begin with the strange behavior of particles at the quantum scale, where reality refuses to behave the way our everyday experience tells us it should. From there, we will move through the mathematical frameworks that describe these phenomena. Frameworks that, when followed to their logical conclusions, predict the existence of parallel worlds. And finally, we will arrive at the concept of eternal inflation, a process that may be generating new universes at every moment, forever, in a space far beyond anything we can observe. This is not science fiction. These are serious proposals, born from equations, debated by physicists, and grounded in the same mathematics that accurately describes the world around you. If these quiet explorations help you rest, they give your mind something vast and calm to settle into as you drift toward sleep, please consider liking and subscribing. It helps this channel continue. Now then, let us begin at the smallest scale we know, the quantum realm, where the first hints of something extraordinary first appeared. In the stillness before measurement, before observation, before the universe commits to any particular arrangement of matter and energy, there exists a realm governed by rules that defy ordinary intuition. This is the domain of quantum mechanics, where particles do not occupy single positions, but spread across space like ripples on a pond, where electrons do not travel along definite paths, but instead inhabit clouds of probability, and where the very act of looking changes what is seen. The story begins not with certainty, but with uncertainty, not with particles, but with waves, not with answers, but with amplitudes. At scales smaller than 100 picometers, roughly 1/10,000,000th of a meter, the familiar world dissolves. An electron orbiting a hydrogen nucleus does not circle like a planet around a star. Instead, it exists as a probability distribution, a mathematical object called a wave function, typically denoted by the Greek letter psi. This wave function contains all the information that can ever be known about the electron, yet it does not specify where the electron is. It specifies only where the electron might be found and with what likelihood should anyone choose to look. The probability of finding the electron at any particular location is given by the square of the wave function's amplitude at that point. This is Born's rule, proposed by Max Born in 1926, and it forms one of the foundational principles of quantum theory. If the wave function at a certain position has an amplitude of 0.3, then the probability of detecting the electron there is 0.09, or 9%. The wave function might have significant amplitude across a region spanning several angstroms, meaning the electron genuinely has no single location until measurement forces the issue. This is superposition, the principle that quantum systems exist in multiple states simultaneously until observed. An electron passing through a double-slit apparatus does not travel through one slit or the other. It travels through both, its wave function splitting and recombining, creating an interference pattern on the detector screen that reveals its wave-like nature. This pattern, with its alternating bands of high and low detection probability, cannot be explained if electrons are simply tiny particles following definite trajectories. The spacing of these interference fringes depends on the electron's momentum and the distance between the slits, following the de Broglie relation, where wavelength equals Planck's constant divided by momentum. For an electron moving at 1% the speed of light, this wavelength is approximately 2.4 times 10 to the power of -10 meters, small enough that quantum effects dominate at atomic scales but vanish into insignificance for objects large enough to hold in one's hand. The mathematics describing this behavior relies on complex numbers, quantities with both real and imaginary components. A probability amplitude is not simply a number between 0 and 1. It is a complex number whose magnitude squared gives probability, but whose phase, the angle it makes in the complex plane, determines how different amplitudes combine. When two paths lead to the same outcome, their amplitudes add together before squaring. If the phases align, constructive interference occurs and the probability increases. If the phases oppose, destructive interference reduces the probability, sometimes to 0. This is why the double-slit pattern shows dark bands where electrons almost never arrive, regions where the amplitudes from the two slits cancel precisely. Consider a single photon, a quantum of light with energy equal to Planck's constant times its frequency. A red photon at 700 nanometers carries approximately 1.77 electron volts of energy, while a blue photon at 450 nanometers carries about 2.76 electron volts. When this photon encounters a beam splitter, a half-silvered mirror that reflects 50% of incident light and transmits the rest, something remarkable occurs. The photon does not randomly choose one path or the other. Instead, its wave function splits, with amplitude flowing along both the reflected and transmitted routes. The photon is genuinely in both places at once, a superposition of two spatial states, until a detector registers its arrival and the superposition resolves. This superposition is not merely a statement about human ignorance. It is not that the photon secretly went one way and we simply do not know which. Experiments testing Bell inequalities, first proposed by physicist John Bell in 1964 and confirmed experimentally by Alain Aspect in 1982, demonstrate that no theory assigning definite hidden properties to quantum particles can reproduce all the predictions of quantum mechanics. The superposition is real. The indefiniteness is fundamental. Nature, at its deepest level, does not commit to specific outcomes until forced to do so. The wave function evolves according to precise mathematical rules. Between measurements, it changes smoothly and deterministically, spreading out, interfering with itself, responding to potentials and forces in its environment. This evolution conserves probability, meaning the total chance of finding the particle somewhere remains exactly 100%. The wave function never truly disappears. It merely redistributes, flowing through the mathematical space of possibilities like water finding its level. Yet the wave function is not a wave in ordinary three-dimensional space. For a single particle, it can be visualized as a field spread across the three spatial dimensions. But for two particles, the wave function lives in 6 dimensions. 3 for each particle's possible position. For 3 particles, 9 dimensions. For a system of n particles, the wave function inhabits a 3n dimensional configuration space, a mathematical construct with no direct physical counterpart in the world of everyday experience. A single gram of matter contains roughly 10 to the power of 23 atoms, meaning its complete quantum description requires a wave function in a space of approximately 10 to the power of 24 dimensions. This is why quantum mechanics is so difficult to simulate on classical computers, and why quantum computers, which manipulate superpositions directly, promise such extraordinary computational power. The amplitudes themselves carry physical meaning beyond mere probability. They encode relationships between different possible outcomes, correlations that persist even when particles are separated by vast distances. 2 electrons created together in a spin singlet state remain entangled, their wave function describing a superposition where one spins up and the other down, but neither has a definite spin until measured. Measure one and find it spinning clockwise, and the other, whether across the room or across the galaxy, will be found spinning counterclockwise. This correlation is instantaneous, yet it cannot transmit information faster than light, a subtle distinction that preserves causality while demonstrating the non-local character of quantum reality. The superposition principle applies not just to position and spin, but to every measurable property of quantum systems. An atom can exist in a superposition of energy levels, simultaneously in its ground state and an excited state, until interaction with a photon or another particle collapses it to one or the other. A molecule can exist in a superposition of different vibrational modes, its atoms simultaneously oscillating in multiple patterns. Even macroscopic objects, in principle, can enter superposition states, though the practical difficulties of isolating large systems from environmental interference make such states extraordinarily fragile and short-lived. This fragility hints at deeper questions. Why do we never see chairs or planets in superposition? Why does the quantum world, with its probability amplitudes and interference patterns, give way to the classical world of definite positions and outcomes? The answer lies in the interaction between quantum systems and their environments, a process called decoherence that will reveal itself as the journey continues. But for now, in this foundational moment, the essential truth remains. Reality, at its most fundamental level, is not made of things with definite properties. It is made of possibilities, weighted by complex amplitudes, waiting for the universe to choose. The waiting, it turns out, is not passive. Those possibilities do not simply hang suspended in some timeless void, frozen until observation arrives. They move, they flow, they evolve according to precise mathematical rules, and the equation that governs this evolution stands as one of the most successful predictions in all of physics. In 1926, the Austrian physicist Erwin Schrödinger published a paper that would reshape humanity's understanding of matter itself. The equation he introduced, now bearing his name, describes how the wave function of a quantum system changes over time. It is not a guess or an approximation. It is exact, deterministic, and has been verified to extraordinary precision across nearly a century of experiments. When physicists calculate the energy levels of hydrogen atoms using Schrödinger's equation, they obtain values that match experimental measurements to better than 1 part in a billion. The equation itself carries a deceptive simplicity in its structure. On one side sits the rate of change of the wave function with respect to time, multiplied by the reduced Planck constant, approximately 1.055 times 10 to the power of minus 34 joule-seconds, and by the imaginary unit I. On the other side sits what physicists call the Hamiltonian operator acting on the wave function. The Hamiltonian encodes all the information about the system's energy: kinetic energy from motion, potential energy from forces, interactions between particles. Everything that determines how the system behaves is contained within this single mathematical object. What makes this equation remarkable is its linearity. If one wave function represents a valid solution and another wave function represents a different valid solution, then any combination of these two, any superposition, is also a valid solution. This mathematical property is not merely a convenience, it is the reason superposition exists at all. The equation permits it. The equation demands it. When a particle exists in a superposition of being in two places, Schrödinger's equation treats both components of that superposition with perfect equality, evolving each according to the same rules, never favoring one possibility over another. Consider an electron bound to a hydrogen atom. The wave function that describes this electron does not specify a single orbit, a single trajectory around the nucleus. Instead, it spreads out into what physicists call orbitals, probability clouds that indicate where the electron might be found if measured. The ground state orbital, the lowest energy configuration, forms a spherical cloud centered on the proton, with the probability density highest at the nucleus and falling off exponentially with distance. The characteristic size of this cloud, the Bohr radius, measures approximately 5.29 times 10 to the power of minus 11 meters, about 50,000 times smaller than the wavelength of visible light. Schrödinger's equation explains why this orbital has this particular shape. The electron's wave function must satisfy the equation while also remaining normalizable, meaning the total probability of finding the electron somewhere must equal exactly 1. These constraints, combined with the specific form of the electromagnetic potential energy between electron and proton, select out only certain allowed solutions. The energy of the ground state works out to negative 13.6 electron volts, meaning that much energy would be required to remove the electron entirely from the atom. Higher energy states exist as well, each with its own characteristic shape, each a solution to the same fundamental equation. The evolution prescribed by Schrödinger's equation is smooth and continuous. A wave function does not jump or skip. It flows like water, changing gradually from one configuration to another. If an electron starts in a superposition of two energy states, the equation describes exactly how the relative phases of those states rotate over time. The frequency of this rotation depends on the energy difference between the states, following the relation E equals h times F, where h is Planck's constant at 6.626 times 10 to the power of minus 34 joule-seconds, and F is the frequency. For typical atomic transitions, these frequencies fall in the range of 10 to the power of 14 to 10 to the power of 15 Hz, corresponding to visible and ultraviolet light. This phase rotation has physical consequences. When two components of a superposition have different energies, their phases rotate at different rates. The interference between them oscillates in time, creating what physicists call quantum beats. These beats have been directly observed in experiments, confirming that the wave function evolution predicted by Schrödinger's equation corresponds to something real, something measurable. Yet the equation contains a profound puzzle. It describes evolution that is completely deterministic. Given the wave function at any moment, the equation specifies exactly what the wave function will be at any future moment. There is no randomness in this evolution, no probability, no uncertainty. The wave function flows forward in time as inevitably as a river flows downhill. If this were the complete story, if Schrödinger's equation governed all physical processes, then the universe would be entirely predictable. Every future state would follow necessarily from every past state. But measurements introduce something else entirely. When a physicist measures the position of an electron, the wave function does not continue its smooth evolution. Instead, it appears to collapse, to suddenly localize around the measured position, abandoning all the other possibilities that existed moments before. This collapse is not described by Schrödinger's equation. It is not smooth or continuous. It is abrupt, random, and irreversible. The probability of finding the electron at any particular position is given by the square of the wave function's amplitude at that position, a rule known as the Born rule after physicist Max Born, who proposed it in 1926. The tension between these two processes, the smooth deterministic evolution and the sudden probabilistic collapse, defines what physicists call the measurement problem. Schrödinger himself recognized this difficulty almost immediately. His famous thought experiment involving a cat in a box was designed not to celebrate quantum mechanics, but to highlight what he saw as its absurdity. If quantum superposition applies to atoms and atoms make up cats, then why should cats not exist in superpositions of alive and dead? The equation permits it. Nothing in the mathematics forbids it. For decades, the standard response was to draw a line between the quantum and classical worlds, to assert that Schrödinger's equation applies only to microscopic systems, while macroscopic objects obey different rules. But this response raises more questions than it answers. Where exactly is this line? How many atoms must a system contain before it stops being quantum? The equation itself provides no guidance. It applies equally well to single electrons and to collections of 10 to the power of 23 particles. The mathematics does not care about size. The wave function, as it evolves under Schrödinger's equation, explores a mathematical space of staggering dimensionality. For a single particle moving in 3 dimensions, the wave function assigns a complex number to every point in space, requiring an infinite amount of information to specify completely. For 2 particles, the wave function lives not in ordinary 3-dimensional space, but in a 6-dimensional configuration space, assigning amplitudes to every possible combination of positions for both particles simultaneously. For n particles, the wave function inhabits a space of 3n dimensions. A single gram of hydrogen contains approximately 6 times 10 to the power of 23 atoms, meaning its wave function technically lives in a space of nearly 2 times 10 to the power of 24 dimensions. This exponential growth in complexity is not a bug, but a feature. It is precisely what allows quantum mechanics to describe entanglement, correlations between particles that have no classical explanation. When two particles become entangled, their joint wave function cannot be written as a simple product of individual wave functions. The whole becomes more than the sum of its parts, and this wholeness is encoded in the high-dimensional structure of the wave function itself. Schrödinger's equation, for all its success, remains a tool whose interpretation divides physicists to this day. Some view the wave function as a complete description of physical reality. Others see it as merely a mathematical device for calculating probabilities with no direct physical meaning. Still others propose that the wave function describes not one reality, but many, each branch of a superposition corresponding to an equally real outcome. These interpretational questions, dormant for much of the 20th century, have returned with new urgency as technology brings quantum effects into ever larger and more complex systems. The equation endures, its predictions confirmed again and again, while the question of what it truly describes remains open, waiting, like the wave function itself, for resolution. The resolution, when it comes, arrives not through deeper mathematics, but through the act of looking. And here, at the boundary between quantum possibility and definite outcome, physics encounters its most persistent puzzle. The measurement problem emerges not as a technical difficulty to be solved with better equipment or more precise calculations, but as a fundamental question about the nature of reality itself. Consider again the electron, that probability cloud spreading through space according to Schrödinger's equation. The wave function evolves smoothly, deterministically, its amplitude shifting in predictable ways as time advances. Nothing in the mathematics suggests any sudden change, any moment of decision. Yet when a detector clicks, when a photographic plate darkens, when any apparatus records the electron's presence, the extended cloud of probability collapses instantaneously to a single point. The electron, which moments before existed as a superposition spread across centimeters or meters, suddenly manifests at one specific location, with probability given by the square of the wave function's amplitude at that point. This collapse, this sudden transition from many possibilities to one actuality, appears nowhere in Schrödinger's equation. The mathematics describes only smooth, continuous evolution. The collapse is something added by hand, a postulate grafted onto the formalism to connect the abstract wave function to the concrete results of experiments. The electron's wave function might assign a 30% probability to finding it in region A and a 70% probability to region B, but after measurement, the electron is simply there, in one place, with no trace of the other possibility remaining. The wave function has not merely been updated to reflect new information. It has undergone a discontinuous, irreversible transformation that the equation itself cannot describe. The Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the late 1920s, offers one response to this puzzle. Rather than treating the collapse as a problem to be solved, Copenhagen embraces it as a fundamental feature of quantum mechanics. The wave function, in this view, does not describe the electron itself, but rather our knowledge of the electron. Before measurement, we possess incomplete information, represented mathematically by the superposition. After measurement, we possess definite information, represented by the collapsed state. The transition reflects not a physical change in the electron, but an update in our knowledge. Bohr insisted on a strict division between the quantum world and the classical world of measuring apparatus. The electron obeys quantum mechanics. The detector, the laboratory, the physicist reading the results, all these belong to the classical realm where objects have definite properties at all times. The measurement process occurs at the boundary between these domains, and the collapse represents the translation of quantum possibilities into classical facts. Bohr never precisely defined where this boundary lies, at what scale or complexity a system transitions from quantum to classical. The ambiguity was, for him, not a flaw but a feature. Physics, he argued, must ultimately be expressed in classical language because that is the language of human experience. The quantum formalism is a tool for predicting the outcomes of experiments, not a picture of reality independent of observation. Heisenberg contributed the uncertainty principle, which places fundamental limits on what can be known simultaneously about a quantum system. The position and momentum of a particle cannot both be determined with arbitrary precision. The product of their uncertainties must always exceed Planck's constant divided by 4 pi, approximately 5.27 times 10 to the negative 35th joule seconds. This is not a limitation of measurement technology, but a feature of nature itself. An electron does not possess simultaneously precise position and momentum. The very concept becomes meaningless at the quantum scale. The Copenhagen interpretation achieved remarkable practical success. It provided clear rules for calculating experimental outcomes, rules that have never failed in nearly a century of testing. The predictions of quantum mechanics, interpreted through Copenhagen, match observations to extraordinary precision. The magnetic moment of the electron, for instance, has been measured and calculated to agree within 1 part in 10 trillion, making it the most precisely verified prediction in all of physics. Whatever philosophical difficulties the interpretation raises, its empirical success is beyond dispute, yet the measurement problem refuses to dissolve entirely. If the wave function represents only knowledge, whose knowledge? When exactly does the collapse occur? If a detector records an electron's position, but no one reads the result for an hour, does the collapse happen when the detector clicks or when the physicist looks? Bohr's answer, that such questions lie outside the domain of physics, satisfied many practitioners but troubled others. The formalism seems to require a special role for observation, for consciousness, for something outside the quantum system that forces it to choose among its possibilities. John von Neumann, in his 1932 mathematical treatise on quantum mechanics, attempted to formalize the measurement process. He distinguished between 2 types of evolution: the smooth deterministic evolution governed by Schrödinger's equation, which he called process 2, and the sudden probabilistic collapse upon measurement, which he called process 1. Von Neumann proved that the collapse could not be derived from the equation, that it represented a genuinely distinct physical process. He also showed that the boundary between the quantum system and the classical measuring apparatus could be placed anywhere along the chain from electron to detector to human brain without changing the final predictions. This result, known as the von Neumann chain, highlighted the arbitrariness of the quantum classical divide. The problem deepens when one considers what constitutes a measurement. A photon striking a photographic plate triggers a chemical reaction, darkening a silver halide grain. Is this a measurement? The grain contains perhaps 10 billion atoms, each interacting with its neighbors through electromagnetic forces. At what point in this cascade of interactions does the wave function collapse? If collapse requires a conscious observer, the grain should remain in superposition until someone looks at the plate. But surely the chemical reaction proceeds regardless of observation. The plate darkens in a sealed box as readily as in an open laboratory. Eugene Wigner proposed, somewhat reluctantly, that consciousness itself might play a fundamental role. In his thought experiment, now known as Wigner's friend, an observer inside a sealed laboratory measures a quantum system and records the result. From the friend's perspective, the wave function has collapsed. But from Wigner's perspective outside the laboratory, the entire system, including his friend, remains in superposition until Wigner himself makes an observation. The two descriptions seem incompatible, yet both follow logically from the Copenhagen rules. Wigner eventually concluded that consciousness must be the trigger for collapse, a position most physicists find unsatisfying, but which the formalism does not clearly exclude. The Copenhagen interpretation, for all its dominance through the mid-20th century, never achieved universal acceptance. Einstein famously objected that God does not play dice, that the probabilistic nature of quantum mechanics must reflect incomplete knowledge rather than fundamental indeterminacy. He spent decades searching for a deeper theory that would restore determinism, never finding one that matched quantum mechanics' predictive power. Schrödinger himself grew uncomfortable with the implications of his equation, devising his famous cat paradox to highlight what he saw as the absurdity of superposition applied to macroscopic objects. A cat in a sealed box, its fate tied to a radioactive decay, would, according to the formalism, exist in a superposition of alive and dead until observed. Surely, Schrödinger argued, this cannot be a correct description of reality. The measurement problem persists because it touches on questions that physics alone may not be equipped to answer. What is the relationship between mathematical formalism and physical reality? Does the wave function describe something real, or is it merely a calculational tool? What role, if any, does observation play in determining outcomes? These questions, raised in the 1920s, remain open today. The Copenhagen interpretation offers one set of answers, pragmatic and empirically successful, but it does so by drawing boundaries that seem arbitrary and by invoking concepts like measurement and observation that resist precise definition. The wave function, evolving smoothly in its infinite dimensional space, carries within it all possible outcomes. Something selects one. The nature of that something remains, after nearly a century, the deepest puzzles in the foundations of physics. The puzzle attracted a young physicist at Princeton in the 1950s, a man who would propose a radical solution by refusing to solve it at all. Hugh Everett III, working under the supervision of John Archibald Wheeler, looked at the measurement problem and asked a question that seemed almost naive in its simplicity. What if nothing special happens during measurement? What if the wave function never collapses? The idea emerged from a willingness to take the mathematics seriously. More seriously, perhaps, than its creators had intended. Schrödinger's equation describes the evolution of quantum systems with perfect determinism. Given the wave function at any moment, the equation specifies exactly what the wave function will be at any future moment. No randomness enters, no probabilities appear. The mathematics flows smoothly, continuously, inevitably forward through time. Yet the Copenhagen interpretation insists that this smooth evolution suddenly stops, replaced by a discontinuous jump to a definite outcome whenever measurement occurs. Everett found this interruption troubling. Why should the fundamental equation of quantum mechanics apply everywhere except during the act of observation? The conventional answer invoked a division between the quantum world and the classical world, between microscopic systems governed by superposition and macroscopic measuring devices that somehow exist outside quantum rules. But this division, Everett recognized, has no basis in the physics itself. A measuring device is made of atoms. Those atoms obey quantum mechanics. The electrons in a Geiger counter, the photons striking a detector, the neurons firing in an observer's brain, all of these are quantum systems. If quantum mechanics is universal, if it applies to everything, then measuring devices must also exist in superpositions. Observers must also be described by wave functions. This realization led Everett to a startling conclusion. Consider again the electron passing through both slits simultaneously, existing in a superposition of left and right. When a detector measures which slit the electron traversed, the Copenhagen interpretation says the superposition collapses to one definite outcome. But Everett proposed something different. The detector, being a quantum system, does not force the electron into a single state. Instead, the detector itself enters a superposition. One branch of the detector's wave function records the electron going left. Another branch records the electron going right. Both outcomes occur. Both are equally real. The mathematics supporting this view follows directly from Schrödinger's equation, applied without exception. When two quantum systems interact, their wave functions become entangled, correlated in ways that cannot be described by treating each system separately. The combined system of electron plus detector evolves into a superposition of correlated states. In one component, the electron went left and the detector registered left. In another component, the electron went right and the detector registered right. Nothing in the mathematics selects one component over the other. Nothing causes one to become real while the other fades into mere possibility. Both persist, both evolve, both continue forward through time according to the same deterministic equation. Everett extended this reasoning to include the observer. A physicist reading the detector also becomes entangled with the system. The physicist's brain enters a superposition, one branch perceiving the left outcome, another branch perceiving the right outcome. Each branch contains a complete, self-consistent experience. Each branch contains a physicist who remembers setting up the experiment, who remembers watching the measurement, who now contemplates a single definite result. Neither branch is privileged, neither is more real than the other. The universe, in Everett's picture, contains both. This is the many worlds interpretation, though Everett himself did not use that phrase. He called his theory the relative state formulation, emphasizing that quantum states only have meaning relative to other quantum states. The electron's position is defined relative to the detector's reading. The detector's reading is defined relative to the observer's perception. There is no absolute, observer-independent fact about which outcome occurred, because all outcomes occur, each in its own branch of an ever-expanding wave function. The branching happens constantly, not just in physics laboratories, but everywhere quantum events unfold. Every radioactive decay, every photon absorption, every molecular collision creates new branches. The number of branches grows exponentially. After a single second, the universal wave function contains more branches than there are atoms in the observable universe. After a minute, the number exceeds any meaningful comparison. The mathematics describes not one universe, but an inconceivably vast collection of parallel realities, all equally real, all coexisting within the same wave function, separated not by space or time, but by the quantum mechanical phenomenon of decoherence. Everett completed his doctoral thesis in 1957, presenting these ideas in a compressed form that ran to only 36 pages. The reception was mixed at best. Niels Bohr, the architect of the Copenhagen interpretation, remained unconvinced. Many physicists found the multiplication of realities extravagant, a violation of Occam's razor that postulated countless unobservable worlds to avoid the single mystery of wave function collapse. Everett, discouraged by the response, left academic physics entirely. He spent the rest of his career working on classified military research and operations analysis, rarely discussing his quantum mechanical ideas. Yet the interpretation refused to disappear. In the 1970s, physicist Bryce DeWitt championed Everett's work, coining the term many worlds and bringing the ideas to a wider audience. The interpretation gained adherents slowly, particularly among cosmologists who needed a version of quantum mechanics that could apply to the universe as a whole. The Copenhagen interpretation, with its reliance on external observers and measuring devices, becomes problematic when the system under study is everything that exists. Who observes the universe? What lies outside to perform measurements? The many worlds interpretation sidesteps these questions by eliminating the need for external observers altogether. The mathematics remains the same as standard quantum mechanics. The predictions for any experiment are identical. The probabilities calculated by the Born rule emerge from the structure of the branching wave function, though explaining exactly how probability arises in a deterministic theory, where all outcomes occur, remains an active area of research. Some physicists argue that the apparent randomness of quantum mechanics reflects the observer's uncertainty about which branch they will find themselves in after measurement. Others invoke decision-theoretic arguments about how rational agents should behave when facing quantum branching. The debate continues, but the empirical content of the theory matches observation precisely. What Everett proposed, in essence, was a trade. He eliminated the mysterious collapse of the wave function, the discontinuous jump that interrupts the smooth evolution described by Schrödinger's equation. In exchange, he accepted the existence of countless parallel branches, each as real as the one we experience. Whether this trade represents progress depends on what one finds more troubling: a universe that contains inexplicable discontinuities, or a universe that contains unobservable copies of everything. The mathematics cannot decide between these options. Both interpretations make the same predictions. The choice, if it is a choice, lies elsewhere. The choice may lie elsewhere, but the mechanism does not wait for philosophical resolution. Something happens at the boundary between quantum and classical, something physical, something measurable, something that explains why we never see cats suspended between life and death, why laboratory instruments always display definite readings, why the world presents itself to us as a single coherent narrative rather than a blur of superposed alternatives. This something has a name. Physicists call it decoherence, and its discovery transformed the interpretation debate from metaphysical speculation into quantitative science. The process begins with a recognition that no quantum system exists in perfect isolation. The electron in its superposition of spin states, the photon traveling through both slits simultaneously, the radioactive atom poised between decay and stability. None of these systems float in an abstract mathematical void. They inhabit a universe dense with other particles, with electromagnetic fields, with thermal radiation, with the constant gentle pressure of their environment. And this environment, crucially, is also quantum mechanical. It too can become entangled with the system under observation. It too can carry away information about which alternative the system has chosen. Consider a single particle in a superposition of two position states, located here and located there, with the wave function assigning probability amplitudes to both possibilities. In the idealized mathematics of introductory quantum mechanics, this superposition persists indefinitely, the two position states interfering with each other, producing the characteristic patterns that reveal quantum behavior. But introduce a single photon from the environment, a stray particle of light bouncing off the system, and everything changes. The photon scatters differently depending on whether the particle occupies position 1 or position 2. After the interaction, the photon carries information about the particle's location. The two systems have become entangled. The mathematics of this entanglement follows directly from Schrödinger's equation. No new physics enters, no collapse postulate, no observer with special powers. The wave function of the combined system, particle plus photon, evolves smoothly according to the standard rules. But when we examine only the particle, ignoring the photon that has scattered away into the environment, something remarkable emerges. The interference terms that characterize quantum superposition begin to vanish. The particle behaves less like a quantum system exploring multiple possibilities and more like a classical object occupying a definite position that we simply do not know. The timescales involved stagger intuition. For a dust grain floating in air at room temperature, interacting with the surrounding gas molecules and thermal photons, decoherence occurs in approximately 10 to the negative 31 seconds. This number, 10 to the power of minus 31 seconds, lies so far beyond any conceivable measurement capability that the quantum superposition of the dust grain's position effectively never exists. Before any instrument could possibly detect the interference pattern that would reveal the superposition, the environment has already entangled with the grain, carrying away the phase information that makes interference possible. Wojciech Zurek, working at Los Alamos National Laboratory in the 1980s, developed the mathematical framework that quantifies this process. His calculations showed that decoherence rates depend on the size of the system, the temperature of the environment, and the strength of the coupling between them. For a large molecule like a buckyball containing 60 carbon atoms, decoherence in air at room temperature occurs in roughly 10 to the power of -17 seconds. For a living cell, the timescale drops to 10 to the power of -29 seconds. For anything approaching human scale, the superposition lifetime becomes so vanishingly small that quantum effects at the level of position and momentum become completely unobservable. This explains, with quantitative precision, why the classical world appears classical. The environment acts as a constant, pervasive measuring apparatus, monitoring every particle, every molecule, every object, extracting information about position and momentum, and carrying that information away into the vast reservoir of environmental degrees of freedom. The wave function does not collapse in any fundamental sense. It becomes entangled with an environment so complex, so thermodynamically irreversible, that the interference terms become practically inaccessible. The information still exists, encoded in the correlations between system and environment, but no conceivable experiment could gather enough of the scattered environmental particles to reconstruct the quantum coherence. The connection to Everett's many worlds interpretation emerges naturally from this framework. Decoherence does not select one outcome over another. It does not explain why we observe this particular result rather than that one. What it does explain is why different branches of the wave function no longer interfere with each other, why they become, for all practical purposes, separate and independent realities. Before decoherence, the superposition represents a genuine quantum state where both alternatives coexist and can influence each other through interference. After decoherence, the branches have become entangled with different configurations of the environment. Configurations so complex and so rapidly diverging that no physical process could ever bring them back together. The branching in this picture happens continuously and ubiquitously. Every interaction between a quantum system and its environment creates new entanglements, new correlations, new branches in the universal wave function. The rate of branching depends on the same factors that govern decoherence: the size of the systems involved, the temperature, the coupling strength. In a typical laboratory at room temperature, the number of branching events occurring every second exceeds any number that human notation can comfortably express. The universe, if Everett's interpretation correctly describes reality, proliferates into new versions of itself at a rate that makes exponential growth seem leisurely. Heinz-Dieter Zäh, a German physicist who independently developed many of these ideas in the 1970s, emphasized that decoherence solves what he called the problem of the preferred basis. In the abstract mathematics of quantum mechanics, a superposition can be written in infinitely many different ways. The state representing a particle here, plus a particle there, can equally well be written as a different superposition of states, representing the particle moving left plus moving right. Without some physical mechanism to select a particular basis, the notion of branching into definite alternatives becomes ambiguous. Decoherence provides this mechanism. The environment couples most strongly to certain observables, typically position and momentum for macroscopic objects, and these observables define the branches that become stable and independent. The experimental verification of decoherence came through increasingly sophisticated tests of quantum coherence in mesoscopic systems, objects large enough to contain thousands or millions of atoms, yet small enough to maintain quantum behavior under carefully controlled conditions. Superconducting quantum interference devices, or SQUIDs, demonstrated superpositions of macroscopic current states, with billions of electrons flowing simultaneously in both directions around a loop. The coherence times matched theoretical predictions based on decoherence calculations, confirming that the transition from quantum to classical behavior follows quantitative laws rather than mysterious collapses. More recently, experiments with large organic molecules have pushed the boundary of quantum behavior to ever larger scales. Researchers in Vienna have observed interference patterns from molecules containing over 2,000 atoms, with masses exceeding 25,000 atomic mass units. These experiments require extraordinary isolation from the environment, temperatures approaching absolute zero, and transit times short enough that decoherence does not destroy the interference before it can be measured. Each successful demonstration confirms that quantum mechanics applies without modification to objects of increasing size, with decoherence alone explaining why everyday objects do not exhibit quantum behavior. The picture that emerges from decoherence research neither proves nor disproves the many worlds interpretation. It does, however, make the interpretation more precise, more quantitative, more connected to experimental physics. The branching of reality, if it occurs, happens through a well-understood physical process with calculable rates and measurable consequences. The branches become independent, not through any mysterious collapse, but through the thermodynamically irreversible spread of quantum information into environmental degrees of freedom. The universe, in this view, does not split at moments of conscious observation. It continuously differentiates through the relentless accumulation of environmental entanglement, a process as natural and inevitable as the increase of entropy. The mathematics that describes this continuous differentiation inhabits a space unlike any that human intuition can directly grasp. Not the 3 dimensions of everyday experience, not even the 4 dimensions of space-time that Einstein revealed, but an abstract arena of potentially infinite dimensions where every quantum state finds its home. This is Hilbert space, named for the German mathematician David Hilbert, who formalized its properties in the early 20th century. And within its geometric structure lies the complete description of quantum reality. A single electron, the simplest quantum system one might consider, already requires an infinite-dimensional Hilbert space for its full description, the wave function that specifies the electron's position spreads across all of space, and each point in space corresponds to a different dimension in the mathematical arena. The electron state becomes a vector, an arrow pointing in some direction within this infinite dimensional landscape. The length of this arrow, carefully normalized to equal 1, encodes the total probability of finding the electron somewhere. The direction of the arrow encodes where that probability concentrates, how it spreads, how it flows. When physicists speak of quantum superposition, they speak in the language of vector addition within Hilbert space. A state that represents an electron definitely at position A corresponds to a vector pointing along one axis. A state representing the electron definitely at position B points along a different axis, perpendicular to the first. The superposition of these two possibilities, the electron existing in both locations simultaneously, corresponds to a vector pointing diagonally, partway between the two axes. The angle of this diagonal determines the relative probabilities. An equal superposition tilts at 45 degrees, giving 50% probability to each location. A state with 90% probability at position A and 10% at position B tilts much closer to the A axis, making an angle whose cosine squared equals 0.9. The geometry becomes richer still when one considers multiple particles. 2 electrons, each requiring an infinite dimensional space for its position, together require a Hilbert space whose dimension equals infinity multiplied by infinity. The mathematical operation that combines individual particle spaces into a joint space carries the name tensor product, and it grows dimensions multiplicatively rather than additively. 3 electrons demand infinity-cubed dimensions. A mole of electrons, some 6 times 10 to the 23rd particles, requires a Hilbert space of such staggering dimensionality that no finite number can capture it. Yet the mathematics remains precise, the geometry well-defined, the calculations tractable for systems of modest size. Within this vast arena, the inner product provides the essential tool for extracting physical predictions. 2 vectors in Hilbert space can be multiplied together in a way that yields a single complex number, and the squared magnitude of this number gives the probability that a system in one state will be found in the other upon measurement. Perpendicular vectors, those whose inner product vanishes, represent mutually exclusive outcomes. Parallel vectors represent identical states. The angle between vectors in Hilbert space directly encodes the statistical relationship between quantum possibilities. The evolution described by Schrödinger's equation takes a particularly elegant form in this geometric picture. The wave function does not merely change its shape over time. The vector representing the quantum state rotates within Hilbert space, tracing out a path determined by the system's energy. The Hamiltonian operator, which encodes all the forces and interactions affecting the system, generates this rotation. States of definite energy correspond to vectors that rotate around a single axis, accumulating phase at a rate proportional to their energy, divided by Planck's reduced constant, approximately 1.05 times 10 to the negative 34 joule-seconds. A state with energy of 1 electron volt, about 1.6 times 10 to the negative 19 joules, rotates through a complete cycle, roughly 2.4 times 10 to the 14 times per second. Superpositions of different energy states create more complex rotational patterns. The vector representing such a superposition does not simply spin around one axis, but precesses, wobbles, traces out intricate paths through the high-dimensional space. The interference patterns that emerge in quantum experiments, the bright and dark fringes of electron diffraction, the oscillating probabilities of neutrino flavor change, all arise from this geometric dance of rotating vectors. The phenomenon of decoherence, that spreading of quantum information into environmental degrees of freedom, also finds precise geometric expression. When a quantum system becomes entangled with its environment, the combined system occupies a state in an even larger Hilbert space, the tensor product of system and environment. Tracing out the environmental degrees of freedom, mathematically averaging over all possible environmental states, leaves the system in what physicists call a mixed state rather than a pure state. A pure state corresponds to a single vector in Hilbert space. A mixed state corresponds to a statistical ensemble of vectors, a probability distribution over possible quantum states. The density matrix formalism captures this distinction with mathematical precision. A pure state has a density matrix that squares to itself, a property called idempotency. Its eigenvalues consist of a single one and infinitely many zeros. A mixed state has a density matrix with multiple non-zero eigenvalues, each representing the probability of a different pure state in the ensemble. The von Neumann entropy, calculated as the negative trace of the density matrix times its logarithm, measures the degree of mixing. Pure states have zero entropy. Maximally mixed states have entropy equal to the logarithm of the Hilbert space dimension. Decoherence drives the von Neumann entropy of a quantum system upward, transforming pure superpositions into mixed states that behave classically. The off-diagonal elements of the density matrix, those that encode quantum coherence and interference, decay exponentially as environmental entanglement accumulates. For a macroscopic object interacting with air molecules at room temperature, this decay occurs on time scales of 10 to the negative 30 seconds or faster, far beyond any experimental ability to observe the coherent superposition. The many worlds interpretation finds its most rigorous formulation within this Hilbert space framework. The universal wave function, encompassing all particles and fields throughout the cosmos, corresponds to a single vector in a Hilbert space of inconceivable dimension. This vector never collapses, never jumps, never does anything but rotate smoothly according to Schrödinger's equation. What appears as branching, as the splitting of reality into parallel versions, corresponds to the development of tensor product structure within this single vector. When a measurement occurs, the universal state evolves into a superposition of terms, each representing a different outcome correlated with a different state of the measuring apparatus and observer. These terms become approximately orthogonal in the full Hilbert space, their inner products suppressed by decoherence to values of 10 to the negative 20 or smaller. The geometry of Hilbert space itself enforces their independence. Orthogonal vectors cannot interfere. Observers in one branch cannot detect or influence observers in another. The branches coexist within the same mathematical structure, yet remain as isolated from each other as if they occupied separate universes. The probability rule that Everett sought to derive from pure quantum mechanics connects to the geometry through the concept of measure. The squared amplitude of each branch, the inner product of that branch's vector with itself, determines its weight in the overall superposition. The Born rule, that mysterious prescription for converting amplitudes to probabilities, emerges as a statement about how to count or weight the branches. Various derivations have been proposed, from decision-theoretic arguments about how a rational agent should bet on quantum outcomes, to symmetry arguments about how probability measures should transform under basis changes. The Hilbert space of quantum mechanics extends beyond the finite dimensional spaces of simple examples to encompass the infinite dimensional spaces required for continuous variables and quantum fields. The position of a particle requires a Hilbert space isomorphic to the space of square integrable functions, those functions whose squared magnitude integrates to a finite value. Quantum field theory demands Fock spaces, constructions that accommodate arbitrary numbers of particles through direct sums of tensor products. The Hilbert space of a quantum field theory in a finite volume remains infinite dimensional, and taking the infinite volume limit introduces additional mathematical subtleties that occupied physicists for decades. Within this geometric framework, the parallel realities of the many worlds interpretation become not mystical speculation, but mathematical structure. The branches exist as orthogonal subspaces within a single Hilbert space, their mutual isolation guaranteed by the same inner product that underlies all quantum predictions. The universe does not multiply itself in some metaphysical sense. It explores the geometry of its own state space, a geometry so vast that orthogonal directions can accommodate what appear to be entirely separate realities, each as real as the others, each inaccessible to the others, all coexisting within the eternal rotation of a single quantum state. The rotation continues, moment by moment, the state vector tracing its path through dimensions beyond counting. But the question of counting itself becomes strange when the branches multiply without end. How many realities emerge from a single quantum event? How does one assign probabilities when the number of outcomes stretches toward infinity? The mathematics required to answer these questions pushes beyond ordinary arithmetic into the realm of measure theory, where infinity must be handled with surgical precision. Consider a single electron passing through a Stern-Gerlach apparatus, its spin measured along some chosen axis. The wave function splits into two branches, one for spin up, one for spin down. The Born rule assigns probabilities based on the squared amplitudes, perhaps 70% and 30% if the initial state was prepared at an angle. But in the many worlds interpretation, both outcomes occur. Both branches become real. So what does 70% mean when both possibilities actualize? The answer lies in the concept of measure, a mathematical generalization of length, area, and volume that extends to infinite dimensional spaces. In Hilbert space, the measure of a branch corresponds to the squared norm of its component in the total state vector. A branch with amplitude coefficient of 0.84 carries a measure of approximately 0.7, while a branch with coefficient 0.55 carries measure roughly 0.3. The branches are not equally real in some democratic sense. They carry different weights, different measures, different contributions to the total quantum state. This weighting becomes crucial when the branching continues. After the first measurement, each branch encounters new quantum events, new superpositions, new splittings. The spin-up branch might encounter a photon in superposition, splitting again into sub-branches. The spin-down branch does the same. The tree of possibilities grows exponentially, each generation doubling or tripling or multiplying by factors determined by the dimensionality of each new quantum interaction. After 10 sequential binary measurements, the number of branches reaches 2 to the 10th power, or 1024 distinct realities. After 100 measurements, the count exceeds 10 to the 30th power, more branches than atoms in a human body. After a mere 300 binary splittings, the number of branches surpasses 10 to the 90th power, exceeding the estimated number of particles in the observable universe by a factor of 10 to the 10th power. But the physical world does not proceed through discrete, well-separated measurements. Quantum interactions occur continuously, constantly everywhere. A single gram of matter contains approximately 6 times 10 to the 23rd atoms, each engaged in electromagnetic interactions with its neighbors, each interaction potentially creating new superpositions, new branches. The decoherence timescale for macroscopic objects can be as short as 10 to the negative 40 seconds, meaning that a dust grain floating in air branches into distinguishable realities faster than any physical process could detect. The branching rate of the universe defies comprehension. Estimates suggest that the number of new branches created per second in the observable universe alone could exceed 10 to the power of 10 to the 100, a number so large that writing it in ordinary notation would require more digits than atoms in existence. This is not infinity in the strict mathematical sense, but it approaches infinity so rapidly that the distinction becomes practically meaningless. Yet the mathematics remains well-defined. The total measure of all branches, summed according to the rules of quantum mechanics, always equals exactly 1. This conservation of measure acts like a conservation law, ensuring that probability remains normalized even as the number of branches explodes beyond comprehension. The measure flows from parent branches to daughter branches like water dividing at a river delta. The total volume preserved even as the number of channels multiplies. The formal framework for handling this infinite branching draws on the theory of stochastic processes and branching measures developed in probability theory during the 20th century. A branching process describes a population that reproduces over generations, each individual producing some random number of offspring. The mathematics tracks not individual members, but statistical properties of the entire population, measures and expectations and limiting behaviors as generation count approaches infinity. In the quantum context, each branch plays the role of an individual, and each quantum interaction plays the role of reproduction. The offspring count depends on the dimensionality of the Hilbert space involved in each interaction. A two-state system produces 2 offspring branches. A continuous variable like position produces uncountably many offspring, requiring integration rather than summation to track the measure flow. The measure theoretic formulation resolves apparent paradoxes about probability in many worlds. When a physicist calculates that an electron has 70% probability of being spin-up, They are calculating the measure of the spin-up branch relative to the total. An observer who finds themselves in the spin-up branch has not experienced something 70% likely to happen to them specifically. Rather, 70% of the total measure of observers who performed that measurement find themselves in spin-up branches. The probability describes the distribution of measure across branches, not the chance of one outcome occurring instead of another. This interpretation requires what philosophers call self-locating uncertainty. Before the measurement, an observer knows they will split into multiple copies, one in each branch. They do not know which copy they will become, because the question itself is malformed. They will become all copies. But each copy, after the split, can ask which branch they find themselves in, and the answer to that question follows the Born rule probabilities derived from the measure distribution. The mathematics of this self-locating uncertainty connects to decision theory and the foundations of rational choice. If an observer must make a bet about a future quantum outcome, how should they reason? The answer, derived from careful analysis of measure-weighted expectations, reproduces exactly the betting odds that would be rational if only one outcome occurred with the Born rule probability. The many worlds interpretation, despite its radical ontology, makes identical predictions to standard quantum mechanics for all practical purposes. The infinite branching also raises questions about the structure of time itself. In classical physics, time flows along a single line, past to future, each moment following uniquely from the previous. In many worlds, time branches like a tree, each moment spawning multiple successor moments, the future not a single destination, but an ever-expanding canopy of possibilities. The past remains unique, a single trunk from which all branches grow, but the future fragments into uncountable directions. This branching structure can be represented mathematically as a directed graph or tree, with nodes representing quantum states and edges representing transitions. The graph grows forward in time, never backward, each node potentially connecting to multiple successor nodes. The measure flows along the edges, dividing at each branching point according to the squared amplitudes of the quantum transition. The topology of this branching tree has interesting properties. Any two branches share a common ancestor, a point in the past where they were the same branch before some quantum event split them apart. The time since that common ancestor can be calculated, at least in principle, by tracing back through the branching history. For branches that diverged recently, the common ancestor lies close in the past. For branches that diverged during the early universe, the common ancestor might lie billions of years ago, near the beginning of cosmic time. But the branches never reconnect. Once separated by decoherence, once rendered orthogonal in Hilbert space, the branches evolve independently forever. No physical process can merge two decohered branches back into one. The inner product between them remains zero, their interference terms vanish, and they proceed through time as if the other did not exist. The tree grows only outward, never inward, its branches spreading but never rejoining. This irreversibility connects to the thermodynamic arrow of time and the growth of entropy. Each branching event increases the total complexity of the quantum state, spreading measure across more and more orthogonal directions. The entropy of the branching structure grows monotonically, never decreasing, providing a quantum foundation for the second law of thermodynamics. The past is simple, a single trunk. The future is complex, an infinite canopy. And this asymmetry, built into the mathematics of Hilbert space and decoherence, explains why time seems to flow in one direction only. The asymmetry of time, written into the branching structure of quantum states, finds an echo in the earliest moments of cosmic history. For the universe itself underwent a transformation so rapid, so violent in its expansion, that the very fabric of space stretched faster than light could traverse it. This period, lasting perhaps only 10 to the negative 36 seconds, shaped everything that would follow, seeding the structures that would become galaxies, stars, and the observers who would one day contemplate the mathematics of infinite branching. The story begins with a problem, or rather, several problems that plagued cosmology in the decades following the discovery of the cosmic microwave background radiation. In 1964, Arno Penzias and Robert Wilson detected a faint hiss of microwave radiation coming from every direction in the sky. A remnant glow from when the universe was approximately 380,000 years old and had cooled enough for electrons to bind with protons, allowing photons to travel freely for the first time. This radiation, measured at a temperature of 2.725 Kelvin, displayed a remarkable uniformity. Across the entire observable universe, spanning some 93 billion light-years in diameter today, the temperature varied by only 1 part in 100,000. This uniformity presented a puzzle. Regions of space on opposite sides of the sky, separated by billions of light-years, had never been in causal contact. Light, traveling at 299,792 kilometers per second since the beginning of time, had not had sufficient opportunity to traverse the distance between them. Yet somehow, these disconnected regions had reached the same temperature, the same density, the same state of thermal equilibrium. The standard model of cosmology, with its steady expansion from an initial singularity, offered no mechanism for this coordination. It was as if two strangers on opposite ends of the Earth had independently decided to set their thermostats to exactly the same temperature, down to the 5th decimal place. This became known as the horizon problem. The particle horizon, the maximum distance from which light could have reached any given point since the beginning of the universe, was far smaller than the scales over which uniformity was observed. Something had to explain how distant regions had communicated, had equilibrated, had synchronized their properties before being separated forever by the expansion of space. A second puzzle emerged from the geometry of space itself. General relativity, Einstein's theory of gravitation published in 1915, describes how matter and energy curve the fabric of space-time. The curvature of the universe as a whole depends on its total energy density. If this density exceeds a critical value of approximately 9.47 times 10 to the negative 27 kilograms per cubic meter, space curves back on itself like the surface of a sphere, eventually collapsing in a big crunch. If the density falls below this critical value, space curves the opposite way, like a saddle, expanding forever at an accelerating rate. Only if the density equals the critical value precisely does space remain flat, extending infinitely in all directions like a Euclidean plane. observations indicated that the universe was very nearly flat. The total energy density appeared to match the critical density to within a few percent. But this near equality presented its own mystery. In an expanding universe, any deviation from perfect flatness grows with time. A universe that was slightly curved in its infancy would become dramatically curved as it aged. For the universe to appear flat today, 13.8 billion years after its beginning, it must have started with a density matching the critical value to 1 part in 10 to the 60th power. This fine-tuning seemed absurd, a cosmic coincidence demanding explanation. The flatness problem joined the horizon problem as evidence that something was missing from the standard cosmological model. The universe appeared too uniform, too flat, too precisely calibrated for its properties to have arisen by chance. Some mechanism must have driven these conditions, some process in the earliest moments that smoothed out irregularities and flattened the geometry of space. The solution emerged in 1980, when a young physicist named Alan Guth, working at the Stanford Linear Accelerator Center, proposed that the universe had undergone a brief period of exponential expansion in its first fraction of a second. This expansion, which Guth called inflation, would have stretched a tiny patch of space, far smaller than a proton, to cosmic scales in an inconceivably short time. During this inflationary epoch, space itself expanded faster than the speed of light, not because anything moved through space at superluminal velocities, but because the metric of space itself was stretching, carrying all points away from each other at rates that increased with distance. The physics driving this expansion involved a hypothetical field called the inflaton, a quantum field pervading all of space with an energy density that remained nearly constant even as space expanded. Unlike ordinary matter and radiation, whose energy densities decrease as space stretches, the inflaton field maintained its energy, providing a constant outward pressure that drove exponential growth. The expansion rate during inflation reached staggering values. Space doubled in size every 10 to the negative 37 seconds or so, meaning that in just 10 to the negative 34 seconds, a region smaller than 10 to the negative 26 meters could expand to the size of the observable universe. This rapid expansion solved the horizon problem elegantly. Regions that appear causally disconnected today were once in intimate contact, compressed into a volume small enough for light to traverse many times over. They equilibrated, reached the same temperature and density, and then were swept apart by the inflationary expansion, carried beyond each other's horizons before they could diverge. The uniformity of the cosmic microwave background reflects not a mysterious coordination, but a shared history, a common origin in a patch of space small enough for thermal equilibrium to establish itself. The flatness problem dissolved as well. Inflation stretched space so dramatically that any initial curvature was diluted to insignificance. Imagine inflating a balloon to the size of the Earth. The surface, which curves noticeably at small scales, would appear perfectly flat to an observer standing on it. The curvature stretched beyond detection. Similarly, inflation expanded the universe by a factor of at least 10 to the 26th, smoothing out any primordial curvature and driving the geometry toward perfect flatness regardless of initial conditions. But inflation did more than solve existing puzzles. It made predictions, testable consequences that could confirm or refute the theory. The most significant involved the tiny fluctuations in the cosmic microwave background. Those 1 part in 100,000 variations in temperature that would eventually seed the formation of galaxies. Inflation provided a mechanism for generating these fluctuations through quantum mechanics itself. During the inflationary epoch, the inflaton field experienced quantum fluctuations, tiny random variations in its value from point to point in space. These fluctuations, governed by the uncertainty principle, occurred at scales far smaller than an atom. But the exponential expansion of space stretched these quantum ripples to cosmic dimensions, freezing them into the fabric of space-time as classical density perturbations. Regions where the inflaton field fluctuated to slightly higher values inflated slightly longer, ending with slightly higher density. Regions with lower field values ended with lower density. These density variations, imprinted on space by quantum mechanics and amplified by inflation, became the seeds from which all cosmic structure would grow. The spectrum of these fluctuations, the distribution of their amplitudes across different length scales, follows a precise mathematical form predicted by inflationary theory. The fluctuations should be nearly scale invariant, meaning that their amplitude remains roughly constant across a wide range of sizes, with a slight tilt toward stronger fluctuations at larger scales. The spectral index, denoted n sub s, measures this tilt, with a value of exactly 1 indicating perfect scale invariance. Inflation predicts a value slightly less than 1, around 0.96, reflecting the gradual change in the inflaton field as inflation proceeded. Observations from satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck mission have measured this spectral index with extraordinary precision. The Planck results, published in 2018, found n sub s equals 0.9649 plus or minus 0.0042, in remarkable agreement with inflationary predictions. The universe carries the fingerprint of quantum fluctuations stretched to cosmic scales, a signature of the inflationary epoch written across the sky. The fingerprint demands an explanation, a mechanism capable of producing such precise statistical signatures. The theoretical framework that predicted these observations before they were made emerged from the work of physicists grappling with puzzles that had nothing to do with temperature fluctuations in the microwave sky. The story begins not with cosmology, but with particle physics, with questions about magnetic monopoles and the peculiar smoothness of a universe that had no obvious reason to be smooth at all. Alan Guth, working at the Stanford Linear Accelerator Center in 1979, was not searching for a theory of the early universe. His attention focused on grand unified theories, the ambitious frameworks that sought to merge the strong nuclear force with the electro-weak interaction at energies around 10 to the 15th giga-electron volts. These theories made a troubling prediction. At the extreme temperatures of the early universe, when energies exceeded the grand unification scale, the symmetry between forces would have been unbroken. As the universe cooled and this symmetry shattered, topological defects should have formed, including magnetic monopoles, hypothetical particles carrying isolated north or south magnetic poles. The problem was quantitative and severe. Grand unified theories predicted that monopoles should have been produced copiously, with a density comparable to that of protons and neutrons. The mass of each monopole would have been enormous, around 10 to the 16th times the proton mass, roughly 10 to the negative 8 grams. A universe filled with such objects would have collapsed back on itself long before stars could form. Yet no magnetic monopole has ever been detected, despite decades of searching. The universe appears to contain none at all, or at most a vanishingly small number. Guth's insight came on the evening of December 6, 1979. He realized that if the early universe had undergone a period of exponential expansion, any monopoles produced before or during this expansion would have been diluted to insignificance. The mathematics was straightforward. If space expanded by a factor of 10 to the 26th or more, the density of any pre-existing particles would decrease by a factor of 10 to the 78. Even a universe initially saturated with monopoles would emerge from such expansion essentially empty of them. But the implications extended far beyond the monopole problem. Guth recognized that the same exponential expansion would solve the horizon problem, the puzzle of why regions of the universe separated by distances greater than light could have traveled since the Big Bang, nonetheless share the same temperature to 1 part in 100,000. Before inflation, these regions would have been in causal contact, able to exchange energy and reach thermal equilibrium. Inflation then stretched this equilibrated patch to encompass everything we can observe. The flatness problem found resolution through the same mechanism. General relativity permits universes with positive curvature, like the surface of a sphere, or negative curvature, like a saddle. The observed universe appears flat to extraordinary precision, with a curvature parameter omega differing from unity by less than 1%. Without inflation, this requires the early universe to have been flat to 1 part in 10 to the 60, an initial condition so precise as to demand explanation. Inflation provides that explanation by stretching any initial curvature to insignificance, much as the surface of a balloon appears flat when inflated sufficiently. The mechanism Guth proposed relied on a scalar field, a quantity defined at every point in space that lacks the directional properties of electric or magnetic fields. This inflaton field, as it came to be called, would have been trapped in a false vacuum state, a local minimum of its potential energy that was not the true lowest energy configuration. The energy density of this false vacuum would have remained constant as space expanded, a crucial property that distinguishes it from ordinary matter or radiation, whose densities dilute as the universe grows. Einstein's equations of general relativity dictate that a constant energy density produces exponential expansion. The scale factor of the universe grows as e to the power of h times t, where h is the Hubble parameter during inflation, determined by the energy density of the false vacuum. For typical grand unified theory energy scales, h would have been approximately 10 to the 37th inverse seconds, meaning the universe doubled in size every 10 to the negative 37th seconds. In a mere 10 to the negative 34 seconds, space could expand by the required factor of 10 to the 26th or more. Guth's original model, however, contained a fatal flaw. The transition from false vacuum to true vacuum occurred through quantum tunneling, the formation of bubbles of true vacuum that expanded at nearly the speed of light. But in an exponentially expanding background, these bubbles could never coalesce. New false vacuum was created between them faster than they could grow to fill it. The universe would have emerged not as a smooth, hot plasma, but as a chaotic foam of bubble walls, nothing like the universe we observe. The resolution came from André Linde in Moscow, and independently from Andreas Albrecht and Paul Steinhardt in the United States. Their new inflation model, proposed in 1981 and 1982, replaced the sharp potential barrier of Guth's scenario with a gradual slope. The inflaton field would roll slowly down this slope, like a ball moving through honey, maintaining the exponential expansion not through a trapped false vacuum, but through the field's gradual evolution. Linde's contribution extended further with chaotic inflation, proposed in 1983. This framework required no special initial conditions, no carefully prepared false vacuum state. Instead, Linde showed that inflation could begin from almost any initial configuration of the inflaton field, provided the field value was sufficiently large. In regions where the field exceeded approximately 3 times the Planck mass, around 7 times 10 to the negative 6 grams, the potential energy would dominate over kinetic and gradient energies, and inflation would proceed. The inflaton field's potential energy function determines the detailed predictions of any inflationary model. The simplest possibilities include a mass term, where the potential equals 1/2 m squared times phi squared, with m being the inflaton mass and phi the field value. For this potential to produce the observed amplitude of density fluctuations, the mass must be approximately 10 to the 13 gigaelectron volts, roughly 10 to the negative 6 times the Planck mass. The field must start at values around 15 times the Planck mass and roll down over approximately 60 e-foldings of expansion before inflation ends. The slow roll conditions quantify when inflation can occur. 2 parameters, epsilon and ET, must both be much smaller than unity. Epsilon measures the steepness of the potential relative to its height, while eta measures its curvature. When these conditions are satisfied, the inflaton field changes slowly compared to the expansion rate, and the universe inflates. When they are violated, inflation ends, and the field oscillates around the minimum of its potential. These oscillations convert the inflaton's energy into ordinary particles through a process called reheating. The inflaton field couples to standard model particles, and its oscillations decay into quarks, leptons, and gauge bosons. The temperature after reheating depends on the coupling strengths and can range from 10 to the 9th to 10 to the 15th Kelvin. This hot plasma then evolves according to standard Big Bang cosmology, cooling and forming the structures we observe. The quantum fluctuations that seed these structures arise from the uncertainty principle applied to the inflaton field itself. During inflation, the field experiences random fluctuations on scales smaller than the Hubble radius, the characteristic distance h inverse over which causal physics operates. These fluctuations are continuously generated and then stretched beyond the Hubble radius by the exponential expansion, where they freeze as classical perturbations in the spatial curvature. The amplitude of these perturbations depends on the ratio of the Hubble parameter during inflation to the rate of change of the inflaton field. This ratio, evaluated when observable scales crossed the Hubble radius roughly 50 to 60 e-foldings before the end of inflation, determines the amplitude of the primordial power spectrum. The observed value of approximately 2 times 10 to the negative 9 constrains the combination of inflaton potential and field value at that epoch. The constraints on the inflaton potential extend beyond the amplitude of perturbations. The spectral index, measuring how the amplitude varies with scale, provides additional information about the shape of the potential during the observable window. A perfectly flat potential would produce a scale-invariant spectrum with spectral index exactly equal to 1. The observed value of approximately 0.965, slightly less than unity, indicates that the potential possessed a gentle slope during the relevant epoch, causing the Hubble parameter to decrease slowly as inflation proceeded. But these observations probe only a narrow window of the inflationary epoch, the final 50 to 60 e-foldings that stretched to become our observable universe. The behavior of the inflaton field before this window, during the potentially vast number of earlier e-foldings, remains hidden from direct observation. And it is in this earlier, unobservable regime that the most profound implications of inflationary theory emerge. The key insight arrived through the work of André Linde, Paul Steinhardt, and Alexander Vilenkin in the early 1980s, building on Guth's original framework. They recognized that the conditions required to end inflation locally need not be satisfied everywhere simultaneously. The inflaton field, subject to both classical rolling down its potential and quantum fluctuations, does not evolve uniformly throughout the inflating space. Consider a region where the inflaton field sits high on its potential, driving exponential expansion. The classical tendency is for the field to roll downward, toward the minimum where inflation ends. But quantum fluctuations continuously perturb the field value, sometimes pushing it further down the slope, sometimes pushing it back up. The competition between classical rolling and quantum fluctuations determines the local fate of each region. The crucial calculation involves comparing the classical displacement per Hubble time to the typical quantum fluctuation. The classical velocity of the field, determined by the slope of the potential and the Hubble friction, causes the field to move by an amount delta phi classical in 1 Hubble time. Meanwhile, quantum fluctuations of wavelength comparable to the Hubble radius contribute kicks of magnitude approximately h divided by 2 pi, where h is the Hubble parameter. When the quantum fluctuations exceed the classical rolling, the field undergoes a random walk rather than a deterministic descent. This condition defines the regime of eternal inflation. In regions where the field happens to fluctuate upward, the potential energy, and hence the Hubble parameter, remain high, and these regions continue expanding exponentially. In regions where the field fluctuates downward sufficiently, it eventually rolls to the minimum, and inflation ends locally. The mathematics reveals an extraordinary asymmetry. Regions that continue inflating expand exponentially, their volume growing by a factor of e cubed, approximately 20 every Hubble time. Regions where inflation ends stop expanding exponentially and transition to the slower expansion of a radiation or matter-dominated universe. Even if the probability of continued inflation in any given Hubble volume is less than 1, the exponential volume growth can compensate. Suppose the probability that a given Hubble volume continues inflating after 1 Hubble time is p, where p is less than 1. After 1 Hubble time, the expected number of inflating Hubble volumes is p times e cubed, approximately 20p. If this product exceeds 1, the total inflating volume grows despite the local tendency to end inflation. For p greater than approximately 0.05, eternal inflation proceeds indefinitely. The result is a fractal structure of cosmic proportions. The inflating region never completely converts to non-inflating space. Instead, it continuously spawns pockets where inflation ends, while maintaining an ever-growing volume of still inflating space. These pockets, regions where the inflaton field has rolled to its minimum and released its energy into particles and radiation, are the bubble universes. Each bubble nucleates within the eternally inflating background, a phase transition from the high-energy false vacuum to a lower-energy state. The process resembles the nucleation of bubbles in a superheated liquid, where random thermal fluctuations occasionally create small regions of vapor that then expand. In the cosmological context, quantum fluctuations rather than thermal fluctuations trigger the transitions, and the bubbles expand into the surrounding false vacuum at velocities approaching the speed of light. But here, the analogy with ordinary bubble nucleation breaks down in a crucial way. In a pot of boiling water, the bubbles eventually merge and convert all the liquid to vapor. In eternal inflation, the background space expands faster than the bubbles can grow. The separation between bubbles increases exponentially, faster than light can travel between them. The bubbles never collide, never merge, never consume the inflating background. The geometry within each bubble differs dramatically from the eternally inflating exterior. As the bubble wall expands outward at nearly the speed of light, the interior undergoes its own evolution. The energy released by the inflaton field reaching its minimum converts to particles through a process called reheating, filling the bubble with a hot, dense plasma. This plasma then evolves according to the standard cosmological history, cooling and expanding, forming atoms, then stars, then galaxies. From inside the bubble, the universe appears infinite. An observer within cannot see the bubble wall, which recedes faster than light can travel. The geometry of the bubble interior, described by an open Friedmann-Lemaire-Robertson-Walker metric, extends indefinitely in all spatial directions. Each bubble contains an infinite universe, yet occupies only a finite and ever-shrinking fraction of the total eternally inflating volume. The rate of bubble nucleation depends on the shape of the inflaton potential, specifically on the height and width of any barriers separating different minima. Sidney Coleman and Frank DeLucia calculated the nucleation rate in 1980, finding it proportional to the exponential of -b, where b is the Euclidean action of the instanton describing the tunneling process. For typical potentials, this rate is extraordinarily small, perhaps 1 nucleation per Hubble volume per Hubble time, with probability of order 10 to the -100 or smaller. Yet even such minuscule rates suffice for eternal inflation. the exponential growth of the inflating volume compensates for the exponential suppression of nucleation. If the inflating volume doubles every Hubble time, while the nucleation probability is 10 to the negative 100 per Hubble volume, then after a few hundred Hubble times, nucleation events become common simply because the number of Hubble volumes has grown to 10 to the 100 or more. The resulting structure defies conventional visualization. An infinite number of bubble universes, each itself spatially infinite, embedded in an eternally inflating background that also extends without limit. The bubbles form a foam-like structure, but a foam where bubbles never touch, where new bubbles continuously form, where the total volume of both bubbles and background grows without bound. Within this framework, our observable universe occupies a position of profound modesty. The roughly 90 billion light-years we can observe represents a tiny patch within one bubble, itself one among infinitely many, floating in an eternal sea of exponential expansion. The cosmic microwave background we measure, the galaxies we catalogue, the physical constants we determine, all characterize our particular bubble, our particular realization of the end of inflation. Other bubbles may differ. The inflaton potential may possess multiple minima, each corresponding to different vacuum states with different properties. The process of symmetry breaking as the field settles into its minimum may proceed differently in different bubbles, yielding different particle masses, different force strengths, different effective laws of physics. The landscape of possibilities extends far beyond the single set of constants we observe. The landscape extends in directions that defy ordinary visualization. Not a landscape of hills and valleys in three-dimensional space, but a landscape in field configuration space, where each point represents a possible state of the quantum fields that permeate the universe. The number of dimensions in this abstract terrain corresponds to the number of independent field values and parameters that can vary, potentially hundreds or thousands in the full theory of fundamental physics. String theory, in its various formulations, suggests a landscape of staggering proportions. The number of distinct vacuum states, each representing a self-consistent way for the extra dimensions to curl up and for the fields to arrange themselves, has been estimated at roughly 10 to the 500th power. Written out, this number would require 500 zeros, a quantity so vast that it exceeds the number of atoms in the observable universe by a factor beyond meaningful comparison. Each of these vacua corresponds to a different possible universe, with different effective laws of physics, different particle content, different values for the constants we measure. The concept of a vacuum state requires careful definition. In quantum field theory, the vacuum is not empty space, but rather the lowest energy state of all the fields. Particles appear as excitations above this ground state, ripples in the underlying field configuration. But the key insight is that there may exist multiple local minima in the energy landscape, multiple configurations that represent stable or metastable resting points for the fields. Consider the analogy of a ball rolling on a hilly terrain. The ball will naturally roll downward, seeking the lowest point. But if the terrain contains multiple valleys separated by ridges, the ball may come to rest in a valley that is not the absolute lowest point. It sits in a local minimum, stable against small perturbations, yet separated from the true minimum by an energy barrier it cannot classically surmount. This is the situation of a false vacuum. The fields have settled into a configuration that appears stable, that resists small fluctuations, yet which does not represent the true ground state of the theory. A lower energy configuration exists, separated by a potential barrier. The false vacuum is metastable, persisting for potentially enormous times, yet ultimately susceptible to decay. The decay mechanism operates through quantum tunneling. Just as an electron can tunnel through a potential barrier that classical physics would forbid it to cross, so too can the field configuration tunnel from the false vacuum to the true vacuum. The probability of such tunneling depends exponentially on the height and width of the barrier, measured in appropriate field-theoretic units. For sufficiently tall and wide barriers, the tunneling rate becomes negligibly small, and the false vacuum persists for times vastly exceeding the current age of the universe. The mathematics of vacuum decay was worked out by Sidney Coleman and collaborators in the late 1970s. The tunneling does not occur uniformly throughout space. Instead, it initiates at a point, creating a bubble of true vacuum that then expands outward. The bubble wall accelerates, approaching the speed of light, converting false vacuum to true vacuum as it sweeps through space. The energy difference between the two vacuum states gets deposited in the bubble wall and in the radiation produced as the wall passes. The nucleation rate for such bubbles depends on the bounce action, a quantity calculated from the field potential that characterizes the tunneling probability. For a potential with barrier height phi sub b and characteristic field scale phi sub 0, the nucleation rate per unit volume goes roughly as the exponential of negative b, where b is the bounce action measured in units of Planck's constant. Typical values of b in realistic theories range from hundreds to thousands, making the exponential suppression extraordinarily severe. In the context of eternal inflation, this vacuum decay process takes on cosmic significance. The inflating false vacuum spawns bubble universes through exactly this tunneling mechanism. Each bubble represents a region where the field has transitioned to a lower energy state, where inflation has ended locally, where the conditions for conventional cosmological evolution can proceed. But the landscape contains not just one true vacuum, but potentially 10 to the 500th distinct minima. The false vacuum of eternal inflation may tunnel to any of these, with relative probabilities determined by the respective bounce actions. Different bubbles thus realize different vacua, different effective physics, different values for what we call the fundamental constants. The constants themselves emerge from the geometry of the extra dimensions and the configuration of various fields in the string theory landscape. The fine structure constant, approximately 1/137, which determines the strength of electromagnetic interactions, depends on the size and shape of the compactified dimensions. The ratio of the proton mass to the Planck mass, roughly 10 to the negative 19, reflects the details of how the strong force emerges from the underlying theory. The cosmological constant, measured at approximately 10 to the negative 122 in Planck units, corresponds to the residual vacuum energy in our particular minimum, This last number presents perhaps the deepest puzzle. Naive estimates of the vacuum energy, summing the zero-point fluctuations of all quantum fields up to the Planck scale, yield a value roughly 120 orders of magnitude larger than observed. The measured cosmological constant is not zero, as a perfect cancellation might suggest, but neither is it the enormous value that straightforward calculation predicts. It sits at a tiny but non-zero value, just large enough to cause the observed accelerating expansion of the universe. The landscape offers a potential resolution, though one that many physicists find unsatisfying. Among 10 to the 500th vacua, the cosmological constant takes different values in different minima. Some vacua have large positive values, leading to runaway inflation that prevents any structure from forming. Some have large negative values, causing rapid collapse. Only those vacua with cosmological constants small enough to permit galaxy formation, star formation, and ultimately observers can be observed from within. The value we measure is not explained by any dynamical mechanism, but rather selected by the requirement that we exist to measure it. This anthropic reasoning troubles many researchers. It seems to abandon the traditional goal of physics, which is to explain observed values from first principles. Yet the landscape, if it exists, may simply be the way nature works. The constants may not be calculable from any deeper theory, but rather environmental, varying from place to place in the multiverse, with our observed values reflecting the conditions necessary for our existence. The transitions between vacua need not be one way. A bubble of one vacuum state, expanding through a region of another, may itself contain regions that tunnel to yet a third state. The hierarchy of vacua, with their various energy levels and barrier heights, creates a complex network of possible transitions. Some vacua may be terminal, true minima from which no further decay is possible. Others may be way stations, metastable configurations that eventually transition to still lower states. Our own vacuum may or may not be absolutely stable. Current measurements of the Higgs boson mass at approximately 125 gigaelectron volts, combined with the top quark mass near 173 gigaelectron volts, place our vacuum in a region of parameter space that appears metastable. The effective potential for the Higgs field, extrapolated to very high energies, may turn over and decrease, suggesting that a deeper minimum exists at field values far beyond those we probe in accelerators. If this is correct, our universe exists in a false vacuum, stable on timescales vastly exceeding its current age, yet ultimately susceptible to decay. A bubble of true vacuum could nucleate at any point in space, expanding at nearly the speed of light, fundamentally altering the laws of physics within its interior. The probability of such an event occurring within our observable universe over the next 10 billion years remains negligibly small, offering no practical cause for concern. Yet the theoretical possibility underscores the contingent nature of the physical laws we observe. The contingent nature of physical law points toward a deeper question, one that has occupied theoretical physicists for decades. Why these laws? Why these particle masses, these coupling constants, these specific forces? The standard model of particle physics, for all its predictive success, contains at least 19 free parameters that must be measured experimentally and inserted by hand. The masses of quarks and leptons, the strengths of the fundamental forces, the parameters governing the Higgs mechanism, none of these emerge from first principles. They simply are what they are, determined by some process we do not yet understand. String theory arose from the attempt to unify all fundamental forces within a single mathematical framework, and in doing so, it suggested an answer to this puzzle. The answer involves dimensions beyond the three of space and one of time that we directly perceive. The story begins in 1968, when Gabriele Veneziano discovered a mathematical formula that described certain properties of the strong nuclear force. The formula, based on the Euler beta function, seemed to emerge from nowhere, a piece of pure mathematics that happened to fit experimental data. Within 2 years, Yoichiro Nambu, Holger Besch-Nielsen, and Leonard Susskind independently recognized what the formula was describing. Not point particles, but tiny vibrating strings. A point particle traces a line through space-time as it moves, a world line. A string, being one-dimensional, traces a surface, a world sheet. The mathematics of how these world sheets behave, how they can split and join, how they vibrate in different modes, turned out to encode the interactions of particles. Different vibrational patterns of the same fundamental string correspond to different particles, much as different vibrational modes of a guitar string produce different musical notes. The lowest vibrational mode of a closed string, one that forms a loop, automatically exhibits the properties of a graviton, the hypothetical quantum of the gravitational field. This was unexpected and profound. String theory did not set out to include gravity. Gravity emerged naturally from the mathematics. For the first time, a framework existed that could potentially describe all 4 fundamental forces: gravity, electromagnetism, the strong force, and the weak force, within a single theoretical structure. But the mathematics imposed a strange constraint. For the theory to be mathematically consistent, to avoid certain pathological features called anomalies, space-time could not have 4 dimensions. The original bosonic string theory required 26 dimensions. Later versions incorporating supersymmetry, the superstring theories, required exactly 10 dimensions, 9 of space and 1 of time. This might seem to immediately disqualify the theory. We observe 3 spatial dimensions, not 9, yet the mathematics suggested a resolution. The extra dimensions could be compactified, curled up so small that they escape detection. Consider an ant walking along a garden hose. From the ant's perspective, the hose has 2 dimensions. It can walk along the length of the hose, or it can walk around its circumference. But from a great distance, the hose appears to be merely a one-dimensional line. The circular dimension has become invisible, compactified below the resolution of observation. The extra 6 spatial dimensions of string theory could be similarly compactified, curled into a tiny geometric shape at every point in the 3 large dimensions we perceive. The size of this compactified space would be on the order of the Planck length, approximately 1.6 times 10 to the power of minus 35 meters, far smaller than any distance we can probe with current technology. The highest energy particle collisions at the Large Hadron Collider probe, distances of about 10 to the power of minus 19 meters, still 16 orders of magnitude larger than the Planck scale. The geometry of the compactified dimensions determines the physics we observe in the large dimensions. The shape of this tiny internal space dictates which particles exist, what masses they have, how strongly they interact. The 19 free parameters of the standard model would emerge from the geometry of the extra dimensions, no longer arbitrary inputs, but consequences of a deeper structure. The mathematical objects that describe these compactified spaces are called Calabi-Yau manifolds, named after Eugenio Calabi and Xingtung Yau. These are six-dimensional shapes satisfying specific geometric conditions required for the resulting four-dimensional physics to have certain desirable properties, including supersymmetry at high energies. A Calabi-Yau manifold cannot be visualized directly. 6 dimensions exceed human spatial intuition. But projections and cross-sections reveal intricate, folded structures, surfaces that curve back on themselves in complex patterns. The topology of these manifolds, the number of holes, the way different cycles wind through the space, determines the number of particle generations, the gauge symmetries, the coupling constants. The number of distinct Calabi-Yau manifolds is vast. Early estimates suggested hundreds of thousands of topologically distinct shapes. As mathematical techniques improved, the count grew. Current estimates place the number of Calabi-Yau manifolds suitable for string compactification at approximately 10 to the power of 47 cubed, a number so large it defies comprehension. Each distinct Calabi-Yau manifold yields a different set of physical laws in the large dimensions. Each represents a different possible universe, with different particles, different forces, different constants. The landscape of string theory vacua, the space of all possible compactifications, contains an essentially infinite variety of potential physics. This proliferation initially seemed like a failure. A theory that predicts everything predicts nothing. If any set of physical laws can emerge from string theory, the theory loses its predictive power. The hope had been that string theory would uniquely determine the laws of physics, that the mathematics would permit only one consistent solution matching our universe. Instead, the mathematics permits an enormous multiplicity of solutions. The landscape stretches across dimensions of possibility, each point representing a different way the extra dimensions could curl, a different vacuum state, a different universe. Yet combined with eternal inflation, this apparent weakness transforms into explanatory power. If the inflationary multiverse continually spawns new bubble universes, and if each bubble can realize a different point in the string landscape, then the multiplicity of solutions becomes a feature rather than a bug. The vast landscape provides the variety. Eternal inflation provides the mechanism for exploring it. The compactification of extra dimensions need not be static. The size and shape of the internal space can vary, described by scalar fields called moduli. In the early universe, these moduli fields would have been dynamical, their values not yet settled. As the universe cooled and expanded, the moduli would have rolled toward stable configurations, the extra dimensions settling into their final compactified form. The energy scale at which this compactification occurs is typically assumed to be near the Planck scale, around 10 to the power of 19 giga-electron-volts, far beyond the reach of any conceivable particle accelerator. At such energies, the distinction between the large and small dimensions would blur, the full 10-dimensional structure becoming apparent. Below this scale, the physics appears 4-dimensional, the extra dimensions hidden but still shaping every interaction. The geometry of the internal space also determines the spectrum of possible excitations. Strings can wind around the compact dimensions, their winding number contributing to their effective mass. The quantized momentum modes in the compact directions similarly contribute. A rich spectrum of massive particles emerges, most with masses near the Planck scale, unobservable in current experiments, but potentially leaving subtle signatures in cosmological observations. The spectrum of massive particles, hidden at the Planck scale, hints at something deeper still. For decades, string theorists worked with not one theory but 5, each mathematically consistent, each describing strings propagating in 10 dimensions, yet each apparently distinct. Type 1 strings, open and closed, carrying gauge symmetries on their endpoints. Type 2a and Type 2b, differing in the chirality of their fermionic sectors. The two heterotic theories, combining the left-moving modes of a bosonic string in 26 dimensions with the right-moving modes of a superstring in 10, the extra 16 dimensions compactified on a torus to generate gauge groups of exceptional size. 5 theories, 5 apparently separate frameworks, each claiming to be a candidate for the fundamental description of nature. The resolution came in 1995, when Edward Witten proposed that these 5 string theories were not separate at all, but different limiting cases of a single underlying framework. This framework, which Witten called M-theory, exists not in 10 dimensions, but in 11. The additional dimension, curled into a circle of radius related to the string coupling constant, connects the different string theories through a web of dualities. As the radius of this 11th dimension varies, the theory smoothly interpolates between the different 10-dimensional descriptions. What appeared to be 5 distinct theories revealed itself as 5 windows onto a single, more fundamental structure. The 11-dimensional framework carries profound implications. In 11 dimensions, the fundamental objects are not strings, but membranes. A 2-dimensional membrane, called an M2 brane, sweeps out a 3-dimensional world volume as it propagates through space-time. When one dimension of this membrane wraps around the compact 11th dimension, the membrane appears from the 10-dimensional perspective as a string. The string tension, measured at approximately 10 to the power of minus 34 newtons in natural units, emerges from the membrane tension combined with the circumference of the wrapped dimension. The fundamental string of 10-dimensional theory is revealed as a membrane in disguise. Similarly, M-theory contains 5-dimensional extended objects, M5 branes, whose dynamics govern much of the theory's structure. These branes carry magnetic charge under the 3-form gauge field that permeates 11-dimensional supergravity, the low-energy limit of M-theory. The M2 branes carry electric charge under this same field, the two types of brane related by electromagnetic duality in the higher dimensional sense. The interplay between M2 and M5 branes generates the rich structure of gauge theories and gravity that emerges in lower dimensions. The dualities connecting the 5 string theories take several forms. T-duality relates theories compactified on circles of different radii. A string theory on a circle of radius r proves equivalent to a theory on a circle of radius proportional to the string length squared divided by r. Small and large compact dimensions become physically indistinguishable, the winding modes of one theory mapping to the momentum modes of the other. This duality exchanges Type 2a and Type 2b string theories when applied to a single compact dimension, revealing their deep connection. S-duality operates differently, relating theories at strong coupling to theories at weak coupling. Type 2b string theory exhibits S-duality as a self-symmetry, the theory at coupling constant g equivalent to the theory at coupling 1 over g. The strongly coupled regime, where perturbative calculations fail, maps to a weakly coupled regime where standard techniques apply. This duality extends to the heterotic theories, connecting the SO32 heterotic string at strong coupling to Type 1 string theory at weak coupling. The web of dualities grows more intricate, each connection revealing hidden equivalences. The 11-dimensional supergravity that describes M theory at low energies was discovered long before M theory itself. In 1978, Eugene Kremer, Bernard Julia, and Joel Shirk constructed this theory, finding that 11 dimensions represented the maximum in which supergravity could exist. Above 11 dimensions, the graviton multiplet would necessarily contain fields of spin greater than 2, leading to inconsistencies in the quantum theory. 11 dimensions emerged as a natural ceiling, a maximum framework for supersymmetric gravity. The field content of 11-dimensional supergravity includes the metric tensor, describing the geometry of space-time, a three-form gauge potential, and a gravitino field carrying spin 3/2. The three-form potential couples naturally to M2 branes, just as the electromagnetic potential couples to point particles. Its field strength, a 4-form, satisfies equations of motion analogous to Maxwell's equations, but generalized to higher dimensions. The gravitino, the supersymmetric partner of the graviton, ensures that the theory preserves local supersymmetry, the gauge symmetry that relates bosons and fermions. Compactification from 11 to 4 dimensions proceeds through the geometry of the internal 7-dimensional space. Unlike the 6-dimensional Calabi-Yau manifolds of string theory, M-theory compactifications often employ spaces of G2 holonomy, 7-dimensional manifolds whose geometry preserves exactly 1/4 of the original supersymmetry. The mathematics of G2 manifolds remains less developed than that of Calabi-Yau spaces, their construction more challenging, their moduli spaces less completely understood. Yet these spaces offered the possibility of deriving realistic, 4-dimensional physics from the 11-dimensional framework. The relationship between M theory and the observable universe passes through many layers of compactification and symmetry breaking. The 11-dimensional theory, compactified on a G2 manifold, yields a 4-dimensional theory with n equals 1 supersymmetry, the minimal amount consistent with the phenomenological requirements of particle physics. The gauge groups and matter content depend on the singularities of the G2 manifold, points where the geometry degenerates and enhanced symmetries emerge. Realistic models require manifolds with precisely arranged singularities, their geometry encoding the structure of the standard model. The vacuum energy in M-theory compactifications depends on the fluxes threading the internal dimensions. Quantized units of the four-form field strength can wrap around 4 cycles in the compact space, each configuration contributing to the effective cosmological constant. The number of possible flux configurations grows exponentially with the number of cycles, contributing to the vast landscape of string vacua. Estimates place the number of distinct M-theory vacua at comparable orders to those in string theory, perhaps 10 to the power of 500 or more, each representing a different possible universe with different physical laws. The dynamics of brains in M-theory opens possibilities beyond those available in perturbative string theory. Brain collisions, brain annihilations, the nucleation of brain-anti-brain pairs from the vacuum. These processes can drive cosmological evolution, potentially explaining the origin of inflation or the nature of dark energy. The ekpyrotic scenario, proposed by Paul Steinhardt and Neil Turok, envisions our universe as a brain floating in the 11-dimensional bulk, periodically colliding with a parallel brain to trigger cycles of cosmic evolution. Each collision releases energy, heating the brain and initiating a new phase of expansion. The holographic principle, emerging from studies of black holes in string theory, finds natural expression in M-theory. The entropy of a black hole, proportional to its horizon area measured in Planck units, suggests that the information content of a region of space scales not with its volume, but with its boundary. In M-theory, this principle manifests in the ADS/CFT correspondence, relating gravitational theories in anti-de Sitter space to conformal field theories living on the boundary. The 11-dimensional theory, reduced on various geometries, generates a family of such correspondences, each providing a window into quantum gravity through the lens of ordinary quantum field theory. The ultimate formulation of M-theory remains unknown. No complete, non-perturbative definition exists, only the low-energy supergravity limit and the various string theory limits connected by dualities. The theory reveals itself through its shadows, through the consistent pictures that emerge in different corners of its parameter space. The search for a complete definition continues, driving research into matrix models, into the algebraic structures underlying the dualities, into the mathematical frameworks that might capture the full 11-dimensional dynamics. The shadows cast by M-theory illuminate a particular structure that transforms our understanding of cosmology itself. Among the extended objects inhabiting the 11-dimensional framework, certain configurations possess the remarkable property of confining matter and forces to their surfaces. These are the brains, and their dynamics opens a window onto cosmic origins that differs fundamentally from the standard picture of a singular beginning. A 3-brain, extending through 3 spatial dimensions, can serve as the arena for all familiar physics. The particles of the standard model, the electrons and quarks, the photons and gluons, exist as open strings whose endpoints attach to the brain surface. They cannot escape into the higher dimensional bulk, confined by the fundamental rules of string attachment. Gravity, however, propagates differently. Gravitons emerge from closed strings, loops without endpoints, free to travel through all 11 dimensions. This asymmetry between matter and gravity creates the foundation for brain cosmology. The hierarchy problem, one of the deepest puzzles in particle physics, finds a geometric interpretation within this framework. The weakness of gravity compared to the other forces, a ratio of approximately 10 to the 38, seems inexplicable in conventional physics. Why should the gravitational coupling constant be so extraordinarily small? In the brain picture, gravity only appears weak because it dilutes across extra dimensions. The fundamental gravitational scale might actually approach the electroweak scale, around 1,000 giga-electron volts, with the apparent weakness arising from the large volume of the extra-dimensional space through which gravitons spread. The Randall-Sundrum models, developed in 1999 by Lisa Randall and Raman Sundrum, demonstrate this mechanism with mathematical precision. In their first scenario, two brains bound a slice of 5-dimensional anti-de Sitter space, a geometry with constant negative curvature. The metric between the brains varies exponentially, creating a warp factor that transforms energy scales. A mass of 1 tera-electron-volt on one brain appears as a mass of 10 to the 16 tera-electron-volts when measured from the other brain. The hierarchy emerges not from any fundamental disparity, but from the geometry of the intervening space. The second Randall-Sundrum model goes further, demonstrating that a single brain can localize gravity even with an infinite extra dimension. The warped geometry creates a gravitational potential well, trapping the graviton zero mode near the brain while allowing massive graviton modes to escape into the bulk. The four-dimensional Newton's law emerges as an effective description, valid at distances large compared to the curvature scale of the anti-de Sitter space. At shorter distances, corrections appear, modifications to the inverse square law that experiments continue to probe down to scales of approximately 50 micrometers. The cosmological implications of brain dynamics reach their most dramatic expression in the ekpyrotic scenario, proposed by Justin Khoury, Bert Overoot, Paul Steinhardt, and Neil Turok in 2001. The name derives from the ancient Greek concept of cosmic conflagration, and the physics involves the collision of brains moving through the higher dimensional bulk. Our universe, in this picture, exists on a 3-brain separated from a parallel brain by a small gap in the extra dimension. The brains attract each other through forces mediated by bulk fields, accelerating toward collision. The approach of the brains creates effects observable from within our 3-dimensional world. As the separation decreases, the effective 4-dimensional cosmology undergoes a period of slow contraction. The scale factor shrinks gradually, and quantum fluctuations in the interbrain distance translate into density perturbations on the brain surfaces. These perturbations, generated during the approach phase, carry a nearly scale-invariant spectrum, matching the observed properties of cosmic structure without requiring conventional inflation. The collision itself represents the moment of creation, the event that standard cosmology identifies as the Big Bang. The kinetic energy of the approaching brains converts into radiation and matter confined to the brain surfaces. Temperatures reach values comparable to the fundamental scale, perhaps 10 to the 16 giga-electron volts, initiating the hot, dense phase from which nucleosynthesis and structure formation proceed. The universe does not emerge from a singularity of infinite density, but from a finite energy collision in a pre-existing higher dimensional space. The cyclic model extends this picture into an eternal sequence, After collision, the branes separate, driven apart by a potential energy that mimics dark energy in the four-dimensional effective description. The universe expands and cools, galaxies form and evolve, and eventually the expansion dilutes all structure to negligible density. Then the interbrain potential reverses, the branes begin approaching again, and the cycle repeats. Each collision generates a new period of cosmic evolution, a new chapter in an endless sequence of creation and dissolution. The duration of each cycle spans approximately 1 trillion years, with the current accelerating expansion representing the early stages of the separation phase. The dark energy driving this acceleration arises from the potential energy of the scalar field, measuring interbrain separation, a field called the radion. As the branes move apart, this potential energy dominates the cosmic energy budget, producing the observed acceleration. Eventually, the potential reaches a maximum and turns over, initiating the contraction phase that leads to the next collision. The entropy puzzle that plagues cyclic models in conventional cosmology finds resolution in the brane picture. Each cycle does not recycle the entropy of the previous cycle, but generates new entropy from the collision energy. The entropy per co-moving volume increases with each cycle, but the co-moving volume itself grows exponentially during the dark energy phase. The entropy density at the beginning of each hot phase remains approximately constant, set by the collision physics rather than by accumulated entropy from previous cycles. The perturbation spectrum generated in the ekporotic scenario differs subtly from inflationary predictions. While both produce nearly scale-invariant spectra, the detailed statistics carry distinguishing signatures. Inflation generates perturbations from quantum fluctuations in a rapidly expanding space, producing Gaussian statistics to high precision. The ekporotic mechanism generates perturbations through a different process, the conversion of entropy perturbations to curvature perturbations during the collision, potentially leaving non-Gaussian signatures at detectable levels. The tensor-to-scalar ratio provides another discriminant. Inflationary models typically predict gravitational wave backgrounds with amplitudes related to the energy scale of inflation. The ekporotic scenario, with its contracting pre-collision phase, produces negligible gravitational waves, a tensor-to-scalar ratio many orders of magnitude below current observational limits. The detection or non-detection of primordial gravitational waves in the cosmic microwave background polarization thus carries implications for the choice between these cosmological frameworks. The mathematical structure of brane collisions requires careful treatment of the singularity that occurs when the branes meet. In the simplest models, the collision represents a moment when the effective four-dimensional description breaks down, requiring the full machinery of M-theory for proper analysis. Various approaches address this challenge, including the use of orbifold techniques that treat the collision as a smooth passage through a geometric singularity, and the application of string theory methods that resolve the singularity through stringy effects. The moduli problem presents another challenge for brane cosmology. The positions and orientations of branes in the compact dimensions correspond to scalar fields in the four-dimensional effective theory. These moduli fields, if not properly stabilized, would produce observable variations in the fundamental constants and unacceptable contributions to the cosmic energy density. The mechanisms that stabilize these fields, involving fluxes and non-perturbative effects, must operate consistently with the dynamics required for brane collision and separation. The landscape of string theory intersects with brane cosmology in intricate ways. Different vacuum states correspond to different configurations of branes and fluxes in the compact dimensions. The collision of branes might trigger transitions between vacuum states, changing the effective physical laws in the resulting universe. Each cycle in the cyclic model might explore different regions of the landscape, sampling different values of the cosmological constant and other parameters. The observer's perspective from within a brane universe reveals only indirect evidence of the higher dimensional structure. The extra dimensions remain hidden, curled into spaces too small for direct detection, or warped in geometries that confine ordinary matter. Yet the consequences of brane dynamics manifest in the large-scale properties of the cosmos, in the spectrum of primordial perturbations, in the nature of dark energy, in the ultimate fate of cosmic expansion. The 11-dimensional framework of M-theory, reduced to 4 observable dimensions through the geometry of branes and bulk, provides a stage for cosmic evolution that extends beyond any single beginning or end. The large-scale properties of the cosmos, shaped by brane dynamics and higher dimensional geometry, raise a question that has haunted physics since the earliest precise measurements of fundamental constants. The universe appears fine-tuned, not fine-tuned in the sense of deliberate adjustment, but fine-tuned in the mathematical sense that small changes to certain parameters would render the cosmos unrecognizable, sterile, devoid of the complex structures that characterize our observable reality. Consider the strength of the strong nuclear force, the interaction that binds quarks into protons and neutrons, that holds atomic nuclei together against the electromagnetic repulsion of positively charged protons. The coupling constant of quantum chromodynamics, denoted alpha sub s, takes a value of approximately 0.118 at energy scales, corresponding to the Z boson mass of 91.2 billion electron volts. This number emerges from measurement, not from any known theoretical principle. Yet if this constant were merely 4% larger, the diproton would become stable. 2 protons could bind directly without the mediating presence of neutrons. Hydrogen would fuse catastrophically in the early universe, leaving no fuel for the slow stellar burning that powers stars across billions of years. The universe would contain no long-lived stars, no steady energy sources, no platforms for the gradual assembly of complex chemistry. If the strong force were 4% weaker, the deuteron would become unbound. The first step of stellar nucleosynthesis, the fusion of 2 protons into deuterium, would fail. Stars could not convert hydrogen into helium through the proton-proton chain. The universe would remain a sea of hydrogen, never progressing to the heavier elements that form planets and organic molecules. The window of viability spans perhaps 8% of the parameter space, a narrow corridor through which our universe happens to pass. The electromagnetic force presents similar constraints. The fine structure constant, alpha, measures the strength of electromagnetic interactions between charged particles. Its value, approximately 1/137.036 or 0.0072975, determines the size of atoms, the energy levels of electrons, the chemistry of molecular bonds. If alpha were significantly larger, electrons would spiral closer to nuclei, atoms would shrink, and the energy required to form chemical bonds would increase dramatically. Carbon-based chemistry, with its delicate balance of bond strengths and molecular geometries, would become impossible. If alpha were significantly smaller, electrons would orbit at greater distances, atoms would expand, and the bonds holding molecules together would weaken to the point of instability. The range of alpha values compatible with complex chemistry spans perhaps 10% variation in either direction. The ratio of electromagnetic to gravitational force strengths reveals an even more striking disparity. Gravity, the weakest of the fundamental forces, acts between all massive particles with a strength characterized by Newton's constant, approximately 6.674 times 10 to the power of -11 cubic meters per kilogram per second squared. The electromagnetic force between two protons exceeds their gravitational attraction by a factor of approximately 10 to the power of 36. This enormous ratio allows stars to exist. If gravity were stronger by a factor of 1,000,000, stars would be smaller, hotter, and shorter-lived, burning through their fuel in millions rather than billions of years. If gravity were weaker by a similar factor, matter would never collapse into stars at all, remaining dispersed as thin gas throughout an expanding cosmos. The cosmological constant lambda presents perhaps the most extreme fine-tuning puzzle. This parameter, representing the energy density of empty space, drives the accelerating expansion of the universe. Its measured value, approximately 10 to the power of -12 squared in natural Planck units, defies theoretical expectation. Quantum field theory predicts that vacuum fluctuations should contribute an energy density 10 to the power of 120 times larger than observed. Some mechanism, unknown and unexplained, cancels these contributions to extraordinary precision, leaving only the tiny residual that astronomers detect through the dimming of distant supernovae. If the cosmological constant were merely 10 to the third power, times larger than its actual value, the universe would have expanded too rapidly for galaxies to form. Matter would never have concentrated into the gravitational wells that seed cosmic structure. If lambda were negative and of comparable magnitude, the universe would have recollapsed before stars could ignite. The mass of the electron, approximately 0.511 million electron volts, participates in multiple fine-tuning relationships. The ratio of electron mass to proton mass, about 1/1836, determines the behavior of atoms and molecules. If electrons were heavier, approaching the proton mass, atoms would become unstable, their structure fundamentally altered. If electrons were lighter by a factor of 10, the energy scales of chemistry would shift, disrupting the delicate balance that allows water to remain liquid over a useful temperature range that permits proteins to fold into functional shapes. The masses of quarks, the fundamental constituents of protons and neutrons, exhibit their own fine-tuning. The up-quark mass, approximately 2.2 million electron volts, and the down-quark mass, approximately 4.7 million electron volts, differ by only a few million electron volts. This small difference determines that neutrons are slightly heavier than protons by about 1.29 million electron volts. Because neutrons outweigh protons, free neutrons decay with a half-life of approximately 610 seconds, converting to protons through beta decay. If the mass difference were reversed, protons would decay into neutrons, and hydrogen atoms would be unstable. The universe would contain no ordinary matter as we know it. The anthropic principle, articulated in various forms by physicists including Brandon Carter in 1973, addresses this apparent fine-tuning through a selection effect. The weak anthropic principle notes simply that observers can only exist in universes compatible with the development of observers. This tautology carries physical content when combined with a theory that predicts multiple universes with varying constants. If the string theory landscape contains 10 to the power of 500 distinct vacuum states, each corresponding to different values of physical parameters, then the question shifts from why our constants take their particular values to why we find ourselves in a region of parameter space compatible with our existence. The strong anthropic principle, more controversial and less clearly defined, suggests that the universe must have properties permitting observers to develop at some point. This formulation edges toward teleology, implying purpose or design, and most physicists treat it with skepticism. The weak version suffices for scientific analysis, requiring only that we account for the selection bias inherent in our observations. The landscape of string theory vacua provides a concrete realization of the anthropic framework. Each vacuum state corresponds to a different compactification geometry, a different arrangement of branes, a different pattern of flux, threading through cycles of the compact dimensions. The low-energy physics emerging from each vacuum includes different values of coupling constants, different particle masses, different cosmological constants. Eternal inflation populates this landscape, nucleating bubble universes that sample different regions of the vast parameter space. Most bubbles contain physics incompatible with complex structure. Their cosmological constants are too large, their nuclear forces too strong or too weak, their particle spectra lacking the ingredients for chemistry. These bubbles expand, evolve, and remain forever empty of observers. A tiny fraction of bubbles, perhaps 1 in 10 to the power of 120 or fewer, land in the habitable region of parameter space. Their constants permit stars to form and burn steadily, permit heavy elements to synthesize in stellar cores and disperse through supernova explosions, permit planets to coalesce from debris disks, permit chemistry to proceed through the long sequence of reactions leading to self-replicating molecules. In these rare bubbles, observers eventually emerge and measure the constants of their local physics, finding them fine-tuned for their own existence. The apparent fine-tuning dissolves into selection bias, the inevitable consequence of asking questions in a universe where questions can be asked. The anthropic explanation remains controversial precisely because it shifts the burden of explanation rather than eliminating it. Why does the landscape exist? Why does eternal inflation populate it? Why do the mathematical structures of string theory permit such a vast range of possibilities? These questions push the mystery back one level without resolving it. Yet the anthropic framework makes predictions, at least in principle. It predicts that observed constants should cluster near the boundaries of the habitable region, not at the center. If the cosmological constant could take any value compatible with galaxy formation, we should expect to measure a value close to the maximum permitted, since larger values correspond to larger volumes of parameter space. The observed value, while small, does appear to sit near the anthropic boundary, consistent with this statistical expectation. The statistical clustering near anthropic boundaries suggests a deeper pattern, one that emerges when we examine not just the cosmological constant, but the full ensemble of physical constants that define our universe. Each constant represents a parameter that could, in principle, take different values across the multiverse landscape. The question becomes not merely why our constants permit life, but how these constants might vary and what mechanisms determine their values in any given pocket universe. The fine structure constant, denoted alpha, measures the strength of electromagnetic interactions. In our universe, alpha equals approximately 1 divided by 137, or more precisely 0.00729735. This dimensionless number governs how strongly electrons bind to atomic nuclei, how light interacts with matter, how chemistry unfolds. A universe where alpha differed by just 4% would alter stellar nucleosynthesis so dramatically that carbon production in stars would become impossible. The resonance in carbon-12 that allows 3 helium nuclei to fuse, the famous Hoyle state at 7.65 million electron volts above the ground state, depends sensitively on the electromagnetic force. Shift alpha upward, and this resonance moves out of the thermal energy range accessible in stellar cores. Shift it downward, and the subsequent reaction converting carbon to oxygen becomes too efficient, leaving no carbon behind. The strong nuclear force, characterized by its own coupling constant of approximately 0.1 at typical nuclear energy scales, binds quarks into protons and neutrons, and binds these nucleons into atomic nuclei. This force operates over distances of roughly 1 femtometer, 10 to the negative 15 meters, and its strength determines nuclear stability. Increase the strong force by just 2%, and the diproton becomes stable. 2 protons would bind directly without needing neutrons, and hydrogen would fuse so rapidly in the early universe that no hydrogen would remain for later star formation. Decrease it by 5%, and the deuteron becomes unbound. Without stable deuterium, the nuclear reaction chains that power stars and synthesize heavy elements would never ignite. The ratio of electromagnetic to gravitational force between 2 protons spans an enormous range, approximately 10 to the 36th power. This hierarchy determines why atoms are small while stars are large, why chemistry operates on scales of angstroms while gravity sculpts structures across light years. The mass of the electron, 0.511 million electron volts, compared to the proton mass of 938.3 million electron volts, establishes atomic structure. Were electrons heavier, atoms would shrink, chemistry would change, and the molecular bonds essential for complex structures might not form with sufficient stability. In the string theory landscape, these constants emerge from the geometry of compactified dimensions. The fine structure constant depends on the volume of certain cycles within the Calabi-Yau manifold, the positions of branes, the values of moduli fields that describe the shape of hidden dimensions. Different compactifications yield different values. The landscape contains perhaps 10 to the 500th distinct vacuum states, each corresponding to a different configuration of extra-dimensional geometry, each producing a different set of low-energy physics. The mechanism by which constants acquire their values involves symmetry breaking during the cooling of each pocket universe. As inflation ends locally and reheating occurs, the inflaton field decays into standard model particles. The energy released, typically around 10 to the 15 or 10 to the 16 giga-electron volts in grand unified theories, drives phase transitions. During these transitions, scalar fields settle into particular minima of their potential energy landscapes. The Higgs field, for instance, acquires its vacuum expectation value of 246 giga-electron volts, giving mass to quarks, leptons, and weak gauge bosons. In another pocket universe, with different initial conditions or a different potential landscape, the Higgs might settle into a different minimum, yielding different particle masses. The cosmological constant itself, measured at roughly 10 to the negative 122 in Planck units, represents the energy density of empty space. In quantum field theory, vacuum fluctuations contribute to this energy. Naive calculations predict a value 120 orders of magnitude larger than observed, the famous cosmological constant problem. The landscape offers a statistical resolution. Among 10 to the 500th vacua, some tiny fraction will have cosmological constants small enough to permit structure formation. We necessarily observe one of these rare configurations. The masses of quarks display their own fine-tuning. The up-quark mass of approximately 2.2 million electron volts and the down-quark mass of roughly 4.7 million electron volts determine that neutrons are slightly heavier than protons by 1.29 million electron volts. This mass difference ensures that free neutrons decay into protons with a half-life of about 10 minutes, while protons remain stable. Reverse this hierarchy, and protons would decay into neutrons. Hydrogen atoms would be unstable. The universe would contain no persistent atomic matter. The Yukawa couplings that determine fermion masses in the Standard Model appear almost randomly distributed across many orders of magnitude. The electron Yukawa coupling is roughly 2 times 10 to the negative 6, while the top quark Yukawa approaches unity. This hierarchy lacks explanation within the Standard Model alone. In string compactifications, these couplings arise from overlap integrals of wave functions in extra dimensions, from the distances between branes where different particle species localize. The apparent randomness reflects the complexity of extra-dimensional geometry. Across the multiverse, each pocket universe samples this parameter space differently. Some universes might have 3 generations of fermions like ours, others might have 4 or 2. Some might have different gauge groups entirely, perhaps lacking the strong force or possessing additional long-range interactions. The Standard Model gauge group, SU of 3 times SU of 2 times U of 1, represents one possibility among many that string theory can accommodate. The variation of constants raises questions about what remains truly constant. In some theoretical frameworks, constants might drift slowly even within a single universe, changing over cosmological time. Observations of distant quasars, whose light has traveled for billions of years, constrain such variations. Measurements of fine structure, constant evolution using absorption spectra of intervening gas clouds, limit changes in alpha to less than a few parts per million over 10 billion years. The constants appear stable within our observable universe, but this stability itself may be a selection effect. The electron-to-proton mass ratio, approximately 1 to 1,836, determines atomic and molecular energy scales. This ratio sets the spacing of vibrational and rotational energy levels in molecules, the temperature scales at which chemistry becomes active. Life as we understand it requires liquid water, which exists in a narrow temperature range determined ultimately by molecular binding energies that depend on this mass ratio. The number of spatial dimensions, 3 in our experience, profoundly shapes physics. In 2 spatial dimensions, there are no stable orbits under inverse square forces. Planets could not circle stars. In 4 or more spatial dimensions, inverse square forces become inverse cube or steeper, and again stable orbits become impossible. The 3-dimensionality of space may itself vary across the landscape, with some compactifications yielding effective theories with different numbers of large dimensions. The arrow of time, the asymmetry between past and future, connects to the initial conditions of each pocket universe. The low entropy state at the beginning of inflation, the smooth distribution of energy that preceded structure formation, establishes the thermodynamic arrow. Different pocket universes might begin with different initial conditions, different entropy gradients, potentially different experienced directions of time. These variations paint a picture of physical law as environmental rather than fundamental. What we measure as constants are parameters of our local vacuum, not immutable features of ultimate reality. The deeper laws, perhaps the principles of string theory or some yet undiscovered framework, remain constant across the multiverse. But their low-energy manifestations, the physics we probe in laboratories and observe in the cosmos, represent one realization among countless possibilities, a single point in an almost incomprehensibly vast parameter space. The recognition that our observed physics represents one environmental realization among many leads naturally to a systematic classification of parallel realities. The cosmologist Max Tegmark, working at the Massachusetts Institute of Technology, developed a taxonomy that organizes the various multiverse concepts into 4 distinct levels, each more radical than the last, each grounded in different physical and mathematical principles. The first level requires no new physics at all. It emerges directly from the standard cosmological model combined with the apparent infinity of space. If the universe extends forever beyond our cosmic horizon, currently located approximately 46 billion light-years away, then the implications become mathematically inescapable. In an infinite space with finite possible quantum states, every possible configuration of matter must eventually repeat. The number of possible arrangements of particles within a Hubble volume, while enormous, remains finite. Estimates place this number around 10 raised to the power of 10 raised to the power of 118, a number so large that writing it in standard notation would require more digits than atoms in the observable universe, yet still finite against infinity. Somewhere in this endless expanse, approximately 10 to the power of 10 to the power of 118 meters away, statistical mechanics guarantees the existence of a region identical to our observable universe in every detail. Every particle occupies the same position. Every quantum state matches precisely. This is not speculation about exotic physics, but a straightforward consequence of combining infinite space with the finite information content of any bounded region. The parallel versions of familiar structures exist not in other dimensions or alternate timelines, but simply very far away, separated by distances that dwarf any scale previously contemplated. The Level 1 multiverse requires only that space continue beyond what light has had time to reach us. Inflation naturally produces this condition, stretching space to sizes vastly exceeding the observable horizon. The uniformity of the cosmic microwave background, with temperature fluctuations of merely 1 part in 100,000, suggests that the same physics operates throughout this extended volume. The parallel worlds of Level 1 share our physical laws, our constants, our vacuum state. They differ only in the particular arrangement of matter, the specific outcomes of quantum events, the accidents of initial conditions. The second level encompasses the bubble universes of eternal inflation, the pocket cosmoses discussed in previous considerations. Here the parallel realities differ more profoundly. Each bubble nucleates with its own vacuum state, its own compactification of extra dimensions, its own values for what we perceive as fundamental constants. The fine structure constant might equal 1 over 137.036 in our bubble, while taking the value 1 over 125 or 1 over 150 in neighboring regions. The cosmological constant, measured here at approximately 10 to the power of minus 122 in Planck units, could be positive, negative, or zero elsewhere in the eternal inflationary background. These Level 2 parallel universes remain causally disconnected from our own. The inflationary expansion between bubbles proceeds faster than light, ensuring that no signal, no traveler, no information can ever pass from one pocket cosmos to another. The multiverse at this level resembles an infinite foam, each bubble containing its own Big Bang, its own cosmic history, its own potential for complexity and structure. The total volume of Level 2 exceeds Level 1, as dramatically as Level 1 exceeds our observable patch. The eternal inflation that generates these bubbles never ends globally, continuously spawning new pocket universes throughout an infinite future. The third level introduces the parallel realities of quantum mechanics itself, the branching worlds proposed by Hugh Everett in 1957. Unlike the spatial separation of Levels 1 and 2, the Level 3 multiverse exists in the abstract mathematical space of quantum states, the infinite dimensional Hilbert space that contains all possible configurations of the universal wave function. When a quantum measurement occurs, when superposition gives way to definite outcomes through decoherence, the wave function branches rather than collapses. All possible results occur, each in its own decohered branch, each equally real within the mathematical formalism. The relationship between Level 3 and the previous levels reveals a subtle redundancy. Tegmark demonstrated that the Level 3 multiverse adds no new physical possibilities beyond what Level 1 already contains. In an infinite space, every possible quantum outcome already exists somewhere, realized in some distant region. The branching of the wave function merely provides an alternative description of the same totality of possibilities. The same physical situations that occur in different quantum branches also occur in different spatial locations within the Level 1 multiverse. The mathematics differs, the conceptual framework differs, but the ensemble of realized possibilities remains identical. This equivalence carries profound implications for the nature of physical reality. Whether we describe parallel versions of events as occurring in distant spatial regions or in separate branches of the wave function, the total set of realized possibilities remains the same. The multiverse, viewed from sufficient abstraction, appears as a single mathematical structure that admits multiple equivalent descriptions. The apparent randomness of quantum mechanics, the unpredictability of measurement outcomes, reflects not fundamental indeterminism, but rather the inability of any observer within the structure to know which branch, which spatial location they inhabit. The fourth level represents the most radical departure from conventional physics. Tegmark proposed that every mathematically consistent structure exists as a physical reality somewhere in the ultimate ensemble. This mathematical universe hypothesis asserts that our universe is not merely described by mathematics, but is itself a mathematical structure, one among infinitely many that possess equal ontological status. The equations of physics do not govern an external physical reality. They constitute that reality. Matter, energy, space, and time are patterns within abstract mathematical relationships. At Level 4, the question of why our universe obeys particular laws dissolves into tautology. We observe the laws we observe because we exist within a mathematical structure that permits observers. Other structures, governed by entirely different axioms, exist with equal validity, but may lack the complexity necessary for self-aware substructures to emerge. The fine-tuning of constants, the apparent design of physical law, becomes a selection effect within the space of all possible mathematics. We necessarily find ourselves in a structure compatible with our existence, regardless of how rare such structures might be in the total ensemble. The evidence for each level varies dramatically. Level 1 follows from established cosmology and requires only that inflation produced a universe larger than our horizon, a near certainty given current observations. Level 2 emerges from the dynamics of eternal inflation, itself a consequence of the same inflationary physics that explains the flatness and uniformity of our observable cosmos. The cosmic microwave background, the distribution of galaxies, the primordial abundance of light elements all support the inflationary paradigm from which Level 2 naturally follows. Level 3 rests on the interpretation of quantum mechanics, a domain where empirical tests remain elusive. The mathematical formalism makes identical predictions regardless of whether one adopts Everett's many worlds view or the Copenhagen interpretation. No experiment has yet distinguished between wave function collapse and wave function branching. The choice between interpretations remains, for now, a matter of theoretical preference, of which mathematical framework one finds more elegant or parsimonious. Level 4 ventures furthest from empirical grounding. The mathematical universe hypothesis makes no unique predictions that distinguish it from more conventional views. Its appeal lies in explanatory completeness, in the elimination of arbitrary initial conditions and unexplained physical laws. If all mathematical structures exist, then nothing requires explanation beyond mathematics itself. The hypothesis achieves maximal generality at the cost of minimal testability. The hierarchy of levels reveals a pattern in the history of physics, a progressive expansion of what we consider real. Copernicus removed Earth from the center of the cosmos. Darwin removed humanity from biological privilege. The multiverse, in its various levels, removes our universe from ontological uniqueness. What once seemed like the totality of existence becomes a local patch, a single bubble, one branch, a particular mathematical structure among endless alternatives. The implications ripple through philosophy, through our understanding of probability, identity, and existence itself. In a multiverse where all possibilities are realized, the concept of probability requires reinterpretation. We cannot ask what might have happened differently when all alternatives actually occur somewhere. We can only ask about the measure, the relative frequency of different outcomes across the ensemble of realizations. This measure problem, the question of how to count and compare infinite sets of possibilities, remains one of the deepest unsolved problems in multiverse cosmology. Yet even as we grapple with the measure problem across infinite realizations, a more radical proposal emerges from the mathematical foundations themselves. The physicist Max Tegmark, building on ideas that trace back to the ancient Pythagoreans and forward through the structural realism of philosophers like Bertrand Russell, poses a question that inverts our usual assumptions about the relationship between mathematics and physical reality. Rather than asking why mathematics describes the universe so effectively, he asks whether the distinction between mathematical structures and physical existence might be illusory altogether. The mathematical universe, hypothesis which Tegmark designates as the Level 4 multiverse, proposes that our physical reality is not merely described by mathematics, but is itself a mathematical structure. Every self-consistent mathematical structure exists in the same sense that our universe exists. The equations are not a map of reality. They are the territory, what we perceive as physical substance, the quarks and electrons, the gravitational fields and quantum states. These are patterns within a mathematical structure, and our consciousness emerges as a self-aware substructure capable of perceiving its own mathematical home from the inside. This proposal rests on a philosophical position called structural realism, which holds that our scientific theories capture real structural relationships in the world, even if we remain uncertain about the intrinsic nature of the entities involved. When physics describes an electron as having charge negative 1.602 times 10 to the power of minus 19 coulombs and mass 9.109 times 10 to the power of minus 31 kilograms, these numbers specify relationships, how the electron interacts with electromagnetic fields, how it responds to forces, how it contributes to atomic structure. The electron is defined entirely by its relational properties, by its place in the mathematical web of physical law. Strip away these relationships, and nothing remains to identify. The same pattern holds throughout physics. A quark is characterized by its color charge, its flavor, its fractional electric charge of plus 2/3 or minus 1/3 the electron charge. A photon is defined by its energy, momentum, polarization, and spin of exactly 1 in natural units. Even space-time itself in general relativity reduces to a 4-dimensional pseudo-Riemannian manifold with metric signature -1, +1, +1, +1. The mathematical structure exhausts the physical content. There is no hidden substance beneath the equations, no mysterious matter that the mathematics merely approximates. Tegmark argues that this realization dissolves the mystery of why mathematics works so well in physics. The unreasonable effectiveness of mathematics, which Eugene Wigner famously puzzled over in 1960, becomes entirely reasonable if physical reality is mathematical structure. We do not discover pre-existing mathematical truths that happen to match an independent physical world. Rather, we are mathematical structures discovering our own properties, like characters in a novel becoming aware of the grammar and syntax that constitute their existence. The hypothesis carries a startling implication. If our universe is one mathematical structure, and if mathematical existence is the only kind of existence, then every consistent mathematical structure must exist with equal ontological status. The integers exist. The real numbers exist. The complex plane exists. Group theory exists. Differential geometry exists. And within each sufficiently complex structure, substructures can emerge that process information, that model their environment, that experience something analogous to consciousness. We are such substructures, embedded in the mathematical framework described by the standard model of particle physics, coupled to general relativity, a structure specified by the gauge group SU of 3 times SU of 2 times U of 1, acting on fermionic matter fields in a curved 4-dimensional spacetime. The Level 4 multiverse thus encompasses all of mathematics. The Level 1 multiverse, with its infinite spatial extent beyond our cosmic horizon, exists as a substructure. The Level 2 multiverse, with its eternally inflating bubbles and varying physical constants, exists as another substructure. The Level 3 multiverse, with its quantum branching and Everettian parallel worlds, exists as yet another. But Level 4 transcends them all, including mathematical structures with entirely different fundamental laws, different dimensionalities, different symmetry groups, structures we might not recognize as physical universes at all. Consider the space of all possible mathematical structures. Some are simple, like the group of integers under addition, characterized by a single binary operation satisfying closure, associativity, identity, and inverse properties. Others are vastly more complex, like the structure of loop quantum gravity with its spin networks and spin foams, or the landscape of string theory vacua with its estimated 1 billion distinct configurations. The mathematical universe hypothesis asserts that complexity and simplicity carry no ontological weight. The integers exist as fully as the standard model. A 2-dimensional cellular automaton exists as fully as 11-dimensional M theory. This radical democracy of existence raises immediate questions about why we find ourselves in this particular structure rather than another. The anthropic principle provides a partial answer. We can only observe structures complex enough to support observers. A universe governed by the trivial group with only a single element and no interesting dynamics, cannot contain self-aware substructures asking questions about their existence. But this constraint still leaves vast numbers of potentially habitable mathematical structures, and we must ask why our experience takes this specific form. Tegmark proposes that the answer involves a measure over mathematical structures, weighted perhaps by simplicity or by some other criterion we have not yet identified. Simpler structures, those requiring fewer bits to specify in some formal language, might dominate the measure, making it more probable that observers find themselves in relatively simple mathematical homes. Our universe, despite its apparent complexity, might represent a local minimum of descriptive complexity among structures capable of supporting life. The Standard Model, with its 18 free parameters and 3 generations of fermions, might be simpler than alternatives that could also produce chemistry and biology. The hypothesis connects to deep questions in the philosophy of mathematics. Are mathematical truths discovered or invented? The mathematical universe hypothesis suggests a third option. Mathematical truths are neither discovered nor invented, but simply are, and we are part of them. The theorem that the square root of 2 is irrational does not describe a fact about an abstract Platonic realm, separate from physical reality. It describes a structural property of the mathematical system we inhabit, as real and concrete as the mass of the proton at 1.673 times 10 to the power of -27 kilograms. Critics raise several objections. The hypothesis seems unfalsifiable, placing it outside the domain of empirical science. If every mathematical structure exists, we cannot test the claim by observing structures that do not exist. Tegmark responds that the hypothesis makes predictions about what we should expect to observe, namely, a universe that is completely describable by mathematics, with no residual physical properties that resist mathematical formulation. Any discovery of genuinely non-mathematical aspects of reality would falsify the hypothesis. Another objection concerns the nature of mathematical existence itself. What does it mean for a mathematical structure to exist? The hypothesis seems to require a form of Platonism, the view that abstract objects have mind-independent reality. But Platonism faces its own philosophical challenges, including questions about how we could have knowledge of abstract objects if they exist outside space and time. Tegmark sidesteps this by denying the distinction between abstract and concrete existence. Our universe is not a concrete instantiation of an abstract mathematical structure. It is the structure, experienced from within. The relationship between consciousness and mathematical structure presents perhaps the deepest puzzle. How does subjective experience arise from abstract relations? The hypothesis suggests that consciousness is itself a type of information processing, a pattern of self-reference and modeling that can occur within any sufficiently complex mathematical structure. The experience of redness, of pain, of wonder at the night sky. These are what certain computational patterns feel like from the inside. The mathematics does not generate consciousness as an additional property. The mathematics, when complex enough, is consciousness. This view connects to integrated information theory, which proposes that consciousness corresponds to integrated information, measured by a quantity called phi. A system with high phi one that cannot be decomposed into independent parts without losing information about the whole, possesses consciousness to a degree proportional to its phi value. The human brain, with its approximately 86 billion neurons and 100 trillion synaptic connections, achieves phi values that remain beyond our current ability to calculate, but presumably rank among the highest in the known universe. Within the mathematical universe hypothesis, every structure with sufficient integrated information contains conscious substructures, experiencing their mathematical home according to its internal logic. Some structures might support forms of consciousness utterly alien to our own, processing information in ways we cannot imagine, experiencing qualities we have no words for. Others might be simpler, supporting only rudimentary awareness, the mathematical equivalent of bacteria or thermostats. The space of possible minds extends far beyond the biological examples we know. The hypothesis also illuminates the nature of physical law. Why does our universe obey consistent mathematical rules? Because it is a mathematical structure, and mathematical structures by definition satisfy their defining axioms. The question of why there is something rather than nothing transforms into the question of why mathematical structures exist. And this question may have no answer beyond the tautologies that consistent structures are consistent. Existence, in this view, is not a property that some things have and others lack. Existence is what it means to be a well-defined mathematical structure. The mathematical structures that constitute reality possess internal relationships that transcend the apparent separations between their components. Within the quantum mechanical framework that underlies our physical universe, these relationships manifest as entanglement, a phenomenon that Einstein famously called spooky action at a distance, but which reveals itself, upon careful analysis, as something far more profound than mere action across space. Entanglement represents correlations woven into the fabric of the wave function itself, correlations that persist regardless of spatial separation, and that, in the many worlds interpretation, extend across the branching structure of reality. The mathematics begins with the tensor product structure of quantum mechanics. When two systems interact, their combined state lives not in the simple union of their individual state spaces, but in the tensor product of their Hilbert spaces. For two particles, each describable by a two-dimensional space of spin states, the combined system inhabits a four-dimensional space. Most states in this larger space cannot be written as simple products of individual particle states. These non-factorizable states are entangled, and they constitute the vast majority of the combined Hilbert space. Entanglement is not the exception but the rule, the generic condition of interacting quantum systems. Consider the singlet state of two spin-1/2 particles, the canonical example that has launched countless experiments and theoretical investigations. The wave function takes the form of one particle being spin up while the other is spin down, minus the reverse configuration, all divided by the square root of 2 for normalization. Neither particle possesses a definite spin direction, yet their spins are perfectly anti-correlated. Measure one along any axis and find it pointing up, the other will be found pointing down along that same axis with certainty. This correlation holds whether the particles are separated by nanometers or by light years. The experimental verification of these correlations has achieved remarkable precision, beginning with Alain Aspect's pioneering experiments in 1982, which tested Bell inequalities with calcium atoms emitting correlated photon pairs. The evidence has only strengthened. Modern experiments using spontaneous parametric down conversion in nonlinear crystals produce entangled photon pairs at rates exceeding 1 million per second. The correlations persist over distances of 1,200 kilometers in satellite-based experiments conducted by the Chinese Michus satellite in 2017. The measured violation of Bell inequalities reaches values of 2.8 when classical physics permits no more than 2.0, confirming that no local hidden variable theory can reproduce quantum predictions. In the many-worlds interpretation, these correlations acquire a new significance. When a measurement occurs on one particle of an entangled pair, the universe branches. But the branching is not independent for the two particles. The correlations encoded in the initial entangled state ensure that branches where one particle shows spin-up are precisely those branches where the other particle shows spin-down. The wave function of the universe, evolving unitarily according to the Schrödinger equation, maintains these correlations across all branches. No information travels between the particles. Instead, the correlations were established when the particles interacted, and they persist as structural features of the branching wave function. This perspective dissolves the apparent paradox of non-locality. In the Copenhagen interpretation, measurement on one particle seems to instantaneously affect the other, raising troubling questions about relativistic causality. In many worlds, nothing is transmitted. Both outcomes occur in different branches, and the correlations simply reflect which branches contain which combinations of results. The universe branches into 4 possibilities: both spin up, both spin down, first up and second down, first down and second up. But the amplitude for the first 2 possibilities is 0 in the singlet state. Only the anti-correlated branches have non-zero amplitude. The correlations are not created by measurement but revealed by it, as the observer becomes entangled with the particles and can only perceive one branch. The phenomenon of decoherence, which drives the branching process, operates through entanglement with the environment. When a quantum system interacts with its surroundings, it becomes entangled with countless environmental degrees of freedom. A single photon scattering off an object carries away information about that object's position, creating entanglement. At room temperature, a dust grain 1 micrometer across becomes entangled with surrounding air molecules at a rate of approximately 10 to the power of 36 scattering events per second. This relentless entanglement suppresses quantum interference between macroscopically distinct states on timescales of 10 to the power of minus 31 seconds for objects of that size. The mathematics of decoherence involves tracing over environmental degrees of freedom. When we cannot access the full quantum state, including the environment, we describe the system alone using a reduced density matrix. For an initially pure superposition, this reduced density matrix rapidly approaches a diagonal form, with off-diagonal coherence terms decaying exponentially. The decoherence rate depends on the square of the separation between superposed states in the relevant basis, explaining why macroscopic superpositions decohere almost instantaneously while microscopic ones can persist. Entanglement entropy quantifies the degree of entanglement between a system and its environment. For a pure state of the combined system, the von Neumann entropy of the reduced density matrix measures how much information about the system has become correlated with the environment. This entropy can reach a maximum of log 2 of d bits for a d-dimensional system, achieved when the system is maximally entangled with its environment. The growth of entanglement entropy during decoherence reflects the spreading of quantum information into environmental degrees of freedom, information that becomes practically inaccessible and effectively lost to any observer confined to the system alone. The monogamy of entanglement constrains how quantum correlations can be distributed. If two particles are maximally entangled with each other, neither can be entangled with any third party. This mathematical property, derivable from the structure of quantum mechanics, has profound implications. It means that entanglement is a limited resource that cannot be freely copied or shared. The Kaufman-Kundu-Wouters inequality quantifies this constraint, showing that the sum of squared concurrences between one particle and all others cannot exceed 1. This monogamy underlies the security of quantum cryptography and shapes the structure of multipartite entangled states. In the many worlds framework, monogamy of entanglement relates to the structure of branching. When an observer measures an entangled particle, they become entangled with it, and by extension, correlated with the distant particle. But this new entanglement between observer and particles respects monogamy constraints. The observer in one branch, having found spin-up, is correlated with the distant particle showing spin-down, but this correlation exists only within that branch. Other branches contain other observers with other correlations. The global wave function maintains consistency across all these relationships. Quantum teleportation exploits entanglement to transfer quantum states between distant locations. The protocol, first proposed by Bennett and colleagues in 1993 and experimentally demonstrated by Zielinger's group in 1997, uses a shared entangled pair and 2 bits of classical communication to transmit an arbitrary quantum state. The original state is destroyed in the process, satisfying the no-cloning theorem. In many worlds terms, teleportation creates correlations between branches such that the receiver's particle ends up in the correct state in each branch, conditional on the classical information received. No faster-than-light signaling occurs because the classical communication is required to complete the protocol. The entanglement between branches themselves presents a more subtle question. In what sense are different branches of the universal wave function correlated? They share a common past, a common wave function before the branching event. The amplitudes of different branches are related by the unitary evolution that created them. But branches cannot directly interact or exchange information after decoherence has occurred. They are like parallel streams that once flowed together but have separated, each carrying the memory of their common origin in the correlations they contain. The quantum Zeno effect demonstrates how observation itself affects entanglement dynamics. frequent measurements can freeze the evolution of a quantum system, preventing it from becoming entangled with other systems. Experiments have confirmed this effect with decay rates suppressed by factors of 50 or more under continuous observation. In many worlds, the Zeno effect arises because frequent measurements cause frequent branching. And in each branch, the system has had little time to evolve between observations. The branches proliferate, but each branch contains a system that has barely changed. Entanglement also connects to the thermodynamic arrow of time through the process of equilibration. An isolated quantum system, even one following deterministic unitary evolution, can appear to approach thermal equilibrium when observed through local measurements. This apparent thermalization arises from entanglement between the observed subsystem and the rest of the system. The entanglement entropy grows, local observables approach their thermal expectation values, and the subsystem behaves as if it has forgotten its initial conditions. The information is not lost, but has spread into correlations that local measurements cannot access. The black hole information paradox brings entanglement to the frontier of theoretical physics. When matter falls into a black hole, and the hole eventually evaporates through Hawking radiation, what happens to the quantum information and entanglement that the matter carried? Hawking's original calculation suggested the radiation was exactly thermal, implying information loss and violation of unitarity. But unitarity is sacred in quantum mechanics, and its violation would undermine the entire framework. Current thinking, influenced by the ADS/CFT correspondence, suggests that information is preserved, encoded in subtle correlations in the Hawking radiation that only become apparent after more than half the black hole has evaporated. The page curve describes how entanglement entropy between a black hole and its radiation should evolve if information is preserved. Initially, as radiation is emitted, entanglement between the hole and radiation grows. But after the page time, roughly when half the initial entropy has been radiated, the entanglement must begin to decrease, eventually reaching zero when evaporation completes. Recent calculations using replica wormholes and quantum extremal surfaces have reproduced this curve, suggesting that space-time geometry itself participates in maintaining quantum correlations. Across the branching structure of the many worlds wave function, entanglement weaves a web of correlations that defines the relationships between all quantum systems. These correlations are not added to reality, but constitute it, the mathematical relationships that give structure to the universal wave function. In this view, what we call particles, fields, and space-time are patterns of entanglement, nodes in a vast network of quantum correlations that spans all branches of reality. The universe is not a collection of separate things, but a single entangled whole, branching endlessly, yet remaining forever one. The entangled wholeness of the quantum state evolves according to Schrödinger's equation, a mathematical law that treats past and future with perfect symmetry. The equation itself contains no preferred direction, no arrow pointing from yesterday toward tomorrow. If we filmed the microscopic dance of quantum amplitudes and played the recording backward, the mathematics would remain equally valid, the evolution equally lawful. Yet our experience of reality unfolds in one direction only, from memory toward anticipation, from cause toward effect, from the low entropy of the early universe toward the thermodynamic equilibrium that awaits in the distant future. This asymmetry between the time-symmetric laws of physics and the time-asymmetric phenomena we observe constitutes one of the deepest puzzles in theoretical physics. Ludwig Boltzmann first glimpsed the resolution in the 1870s when he connected the arrow of time to the statistical behavior of vast numbers of particles. His insight was that entropy, the measure of disorder or the number of microscopic arrangements consistent with a macroscopic state, almost always increases simply because there are overwhelmingly more disordered states than ordered ones. A deck of cards shuffled randomly will almost certainly move from an ordered arrangement toward disorder, not because the laws of physics forbid the reverse, but because disordered arrangements vastly outnumber ordered ones. The mathematics of this statistical tendency is precise and quantifiable. For a system of particles, the number of microstates corresponding to thermal equilibrium exceeds the number corresponding to low entropy configurations by factors that dwarf human comprehension. A gas of 10 to the power of 23 molecules has approximately 10 to the power of 10 to the power of 23 possible arrangements, and the overwhelming majority of these correspond to uniform, featureless equilibrium. The probability of spontaneous entropy decrease in such a system is not merely small, but effectively zero, suppressed by factors like 1 divided by 10 to the power of 20. Yet Boltzmann's statistical explanation raises a puzzle that troubled him until his death and continues to challenge physicists today. If the laws of physics are time-symmetric and statistical mechanics explains why entropy increases toward the future, then by the same logic, entropy should also increase toward the past. Running the statistical argument backward, we should expect that any low entropy state we observe arose from an even higher entropy state through a fantastically unlikely fluctuation. This leads to the disturbing conclusion that our memories of the past are more likely to be false, created moments ago by random fluctuation, than to be accurate records of a genuinely lower entropy history. The resolution to this paradox lies not in the laws of physics themselves, but in the boundary conditions of our universe. The early cosmos, approximately 13.8 billion years ago, existed in a state of extraordinarily low entropy. The cosmic microwave background radiation reveals a universe that was remarkably uniform, with density fluctuations of only 1 part in 100,000. This uniformity represents a gravitationally low entropy state because gravity is attractive, and matter spread uniformly has far fewer arrangements than matter clumped into stars, galaxies, and black holes. Roger Penrose has quantified this initial fine-tuning with startling precision. Comparing the entropy of the early universe to the maximum possible entropy of a universe with the same mass, he estimates that the probability of such a low entropy beginning arising by chance is approximately 1 in 10 to the power of 1,223,000,000. This number is so incomprehensibly small that writing it out would require more zeros than there are particles in the observable universe. The arrow of time, in this view, is not explained by the laws of physics, but by this extraordinary boundary condition, what Penrose calls the past hypothesis. Within the many worlds interpretation, the arrow of time takes on new dimensions of meaning. Each branch of the universal wave function inherits the low entropy boundary condition from the initial state, and each branch experiences its own thermodynamic arrow, pointing from that shared past toward its individual future. The branching process itself is intimately connected to entropy increase, as quantum decoherence transforms pure superpositions into the mixed states that characterize thermodynamic irreversibility. When a quantum measurement occurs, the entanglement between system and environment spreads quantum correlations across countless degrees of freedom. This process increases the von Neumann entropy of the reduced density matrix, describing the system alone, even though the entropy of the total universal wave function remains constant at zero, as befits a pure quantum state evolving unitarily. The apparent entropy increase we observe is a consequence of our limited access to the full quantum state, our inability to track the correlations that spread into the environment. The relationship between branching and entropy suggests that the arrow of time and the direction of branching are fundamentally the same phenomenon, viewed from different perspectives. We remember the past because records and memories are low entropy configurations that can only form when entropy is increasing. We cannot remember the future because the thermodynamic arrow points away from it, and we perceive branching as occurring toward the future because decoherence, like all irreversible processes, follows the thermodynamic arrow established by the past hypothesis. In eternal inflation, the question of time's arrow becomes even more intricate. Each bubble universe nucleates with its own initial conditions, its own low entropy beginning that establishes a local thermodynamic arrow. But the eternally inflating background has no beginning and no end, no global arrow of time that orders all events. Different bubble universes may have thermodynamic arrows pointing in different directions relative to any attempted global time coordinate, though observers within each bubble would experience their local arrow as the natural direction of time. The entropy of our observable universe has increased from approximately 10 to the power of 88 in the early cosmos to roughly 10 to the power of 104 today, with most of this entropy residing in the cosmic microwave background radiation and in supermassive black holes. The largest black holes, with masses exceeding 10 to the power of 10 solar masses, individually contain entropies approaching 10 to the power of 104, calculated using the Bekenstein-Hawking formula that relates black hole entropy to horizon area. As the universe continues to expand and cool, entropy will continue to increase, approaching a maximum value estimated at 10 to the power of 120, when all matter has either fallen into black holes or dispersed into the void. The ultimate fate of entropy in an accelerating universe remains a subject of active research. If dark energy maintains its current density of approximately 6 times 10 to the power of -10 joules per cubic meter, the universe will approach a de Sitter state with a cosmological horizon at roughly 16 billion light-years. This horizon has an associated entropy of about 10 to the power of 122 calculated from its area, representing a maximum entropy bound for our observable patch. Whether this represents a true equilibrium or merely a long-lived metastable state depends on questions about the nature of dark energy and the quantum properties of de Sitter space that remain unresolved. Across the infinite branches of the many-worlds wave function, thermodynamic arrows point consistently from the shared low-entropy past toward diverging futures. Each branch carries the imprint of that primordial order, that extraordinary boundary condition that makes complexity, life, and memory possible. The arrow of time is not written into the fundamental equations, but emerges from the cosmic initial conditions, a contingent feature of our universe that could have been otherwise, yet defines everything we experience as the flow of moments from past through present toward future. The thermodynamic arrow points toward equilibrium, toward the gradual dispersal of energy and the smoothing of gradients that drives all physical processes. Yet this very tendency toward maximum entropy creates a profound puzzle when we consider infinite time scales and infinite spatial volumes. In a universe that persists forever, statistical mechanics makes a disturbing prediction. Random fluctuations will eventually produce any configuration of matter, no matter how improbable, simply because eternity provides unlimited opportunities for the unlikely to occur. Ludwig Boltzmann first recognized this implication in the late 19th century while developing the statistical foundations of thermodynamics. He understood that entropy increases because high-entropy states vastly outnumber low-entropy states in the space of possible configurations. A gas spreads throughout its container not because some force pushes it, but because there are astronomically more ways for molecules to be dispersed than concentrated. The probability of spontaneous concentration is not zero, but merely extraordinarily small, perhaps 1 chance in 10 raised to the power of 10 to the 23rd for a macroscopic volume of gas to spontaneously gather in one corner. Yet in infinite time, even this vanishingly small probability becomes certainty. Given enough duration, random thermal fluctuations will produce any arrangement of particles, including arrangements that constitute observers capable of contemplating their own existence. These hypothetical entities, now called Boltzmann brains, would emerge fully formed from random quantum and thermal fluctuations, complete with false memories of a past that never occurred and perceptions of an orderly universe that exists only in their momentary configuration. The mathematics of this scenario follows directly from statistical mechanics. The probability of a fluctuation decreases exponentially with the entropy reduction required. Creating a human brain with its approximately 10 to the 26th atoms arranged in the precise configuration necessary for consciousness requires an entropy reduction of roughly 10 to the 25th joules per Kelvin. At a temperature of 3 Kelvin, the current cosmic microwave background temperature, the probability of such a fluctuation occurring in any given Planck volume during any given Planck time is approximately 10 to the negative power of 10 to the 25th. This number is so small that writing it in standard notation would require more zeros than there are particles in the observable universe. However, the observable universe contains approximately 10 to the 80th particles, and if the universe persists for infinite time, even this incomprehensibly small probability eventually yields actual occurrences. The expected waiting time for a Boltzmann brain to fluctuate into existence in a volume the size of our observable universe is roughly 10 to the power of 10 to the 25th years, a duration that dwarfs the current cosmic age of 13.8 billion years by a factor beyond meaningful comparison. Yet infinity is larger still. The problem becomes acute when we consider the predictions of eternal inflation. In this framework, the universe does not merely persist for infinite time, but generates infinite spatial volume as well. New pocket universes continuously nucleate from the inflating background, each potentially evolving toward a de Sitter phase dominated by vacuum energy. A de Sitter universe with positive cosmological constant maintains a constant temperature determined by its horizon, the Gibbons-Hawking temperature of approximately 10 to the negative 30 Kelvin for our observed cosmological constant. This temperature is extraordinarily low, but it is not zero, and it persists forever. In such a universe, thermal fluctuations continue indefinitely. The de Sitter horizon radiates particles through a process analogous to Hawking radiation from black holes, maintaining the space at constant temperature despite the exponential expansion. Over sufficiently long time scales, these fluctuations will occasionally produce complex structures, including structures that constitute observers. The calculation suggests that in any given Hubble volume of de Sitter space, a Boltzmann brane will fluctuate into existence approximately once every 10 to the power of 10 to the 22nd years. This creates a disturbing prediction about the nature of typical observers in an eternally inflating multiverse. If we count all observers that will ever exist, the vast majority will be Boltzmann branes rather than evolved biological entities like ourselves. The reason is simple. Biological observers require the extraordinarily special conditions of a low-entropy Big Bang, the formation of galaxies and stars, the synthesis of heavy elements, and billions of years of planetary evolution. Boltzmann branes require only random fluctuations and infinite time. In an infinite universe, the latter vastly outnumber the former. The ratio is staggering. For every observer that emerges through the ordinary process of cosmic evolution, stellar nucleosynthesis, and biological development, there will be approximately 10 to the power of 10 to the 50th Boltzmann branes that fluctuate into momentary existence. If we are typical observers, as the principle of mediocrity suggests we should assume, then we should expect to be Boltzmann branes rather than evolved humans. Yet we have every reason to believe we are not Boltzmann branes. Our memories are consistent with external evidence. Our perceptions match a coherent physical world. And our experiences unfold in a causally connected sequence rather than appearing as isolated moments. This tension between theoretical prediction and observed experience constitutes the Boltzmann brane problem, one of the most serious challenges facing eternal inflation and other cosmological models that predict infinite spatial or temporal extent. The problem is not merely philosophical, but strikes at the heart of scientific methodology. If most observers are Boltzmann branes with false memories and perceptions, then we cannot trust our observations to reflect external reality, and the entire scientific enterprise becomes suspect. Several proposed resolutions address this paradox. One approach questions whether de Sitter space truly persists forever. Quantum effects might cause the vacuum to decay after a finite time, perhaps through tunneling to a state with zero or negative cosmological constant. If the expected lifetime of de Sitter space is shorter than the Boltzmann brane formation time, then the problem dissolves. Current estimates suggest that vacuum decay might occur on time scales of 10 to the power of 10 to the 10th years, potentially short enough to prevent Boltzmann brane domination, though these calculations carry substantial uncertainty. Another resolution involves the measure problem we encountered earlier. Different ways of counting observers in an infinite multiverse yield different predictions about the ratio of Boltzmann branes to ordinary observers. Some measures, such as the causal patch measure that counts only observers within a single observer's causal horizon, naturally suppress Boltzmann branes by limiting the effective volume and time available for fluctuations. The choice of measure thus determines whether Boltzmann branes pose a problem, but this merely shifts the question to which measure correctly describes physical probability. A more radical approach questions whether Boltzmann branes should count as observers at all. A fluctuation that produces a brane-like configuration for a single instant might not constitute genuine consciousness or observation. Perhaps observers require not just the right configuration, but also the right causal history, the right relationship to their environment, or the right duration of existence. These criteria would exclude most Boltzmann branes, while including evolved biological observers, but they require a theory of consciousness that we do not yet possess. The statistical mechanics underlying Boltzmann branes connects to deeper questions about the nature of fluctuations in quantum field theory. In a quantum vacuum, virtual particles constantly appear and disappear, borrowing energy from the uncertainty principle for brief moments. These fluctuations are real in the sense that they produce measurable effects, such as the Casimir force between conducting plates and the Lamb shift in atomic spectra. The energy scale of vacuum fluctuations is set by the Planck energy, approximately 1.22 times 10 to the 19th giga-electron volts, though the effective energy available for macroscopic fluctuations depends on the temperature and the volume considered. The Boltzmann brane problem also illuminates the special nature of our observed universe. The fact that we appear to be evolved observers rather than random fluctuations suggests that our universe began in an extraordinarily low entropy state, the very boundary condition that establishes the thermodynamic arrow of time. This initial condition is itself highly improbable from a statistical perspective, perhaps one configuration among 10 to the power of 10 to the 123rd possible initial states. Yet it is far more probable than the fluctuation required to produce a Boltzmann brane directly, because a low-entropy Big Bang can give rise to countless evolved observers through ordinary physical processes. This observation leads to what might be called the Boltzmann brane bound on cosmological theories. Any acceptable theory of the universe must predict that evolved observers like ourselves are more common than Boltzmann branes, or else the theory undermines its own evidential basis. This requirement constrains the allowed combinations of cosmological constant, vacuum lifetime, and spatial topology in ways that complement other observational constraints. The fact that we exist as evolved observers provides information about the large-scale structure of reality. The fluctuations that would produce Boltzmann branes represent the extreme tail of a probability distribution that also includes smaller, more common fluctuations. Random arrangements of a few particles occur constantly throughout the universe. Slightly more complex fluctuations, perhaps involving a few thousand atoms, occur less frequently but still regularly on cosmic time scales. The probability decreases exponentially with complexity, creating a hierarchy of fluctuation phenomena that ranges from routine quantum events to the nearly impossible emergence of conscious observers. This hierarchy of fluctuation probabilities reveals a deeper puzzle that haunts any attempt to make predictions within an eternally inflating multiverse. When the number of observers, pocket universes, or physical configurations becomes genuinely infinite, the very concept of probability loses its familiar meaning. We cannot simply count favorable outcomes and divide by total outcomes when both quantities diverge to infinity. This is the measure problem, perhaps the most profound conceptual challenge facing modern theoretical cosmology. Consider the seemingly simple question of what fraction of observers in the multiverse inhabit universes with a cosmological constant similar to our measured value of approximately 10 to the power of minus 122 in Planck units. In eternal inflation, pocket universes with every possible vacuum energy nucleate continuously throughout the inflating background. An infinite number of universes with our cosmological constant exist, but so do infinite numbers with every other value. Infinity divided by infinity yields no definite answer. The ratio depends entirely on how we choose to regulate or cut off the infinities, a choice that appears arbitrary from the perspective of fundamental physics. The technical formulation of this problem involves defining a measure on the space of all possible observations. A measure assigns weights to different outcomes, allowing the calculation of probabilities even in infinite spaces. In ordinary quantum mechanics, the Born rule provides such a measure through the squared amplitude of the wave function. But eternal inflation generates a classical ensemble of pocket universes, and no analogous fundamental principle determines how to weight different members of this ensemble. Several proposed measures have emerged from theoretical investigations, each with distinct physical motivations and mathematical properties. The proper time cutoff measure counts observers that form before a given proper time has elapsed since the beginning of inflation. This approach seems natural from the perspective of an imaginary observer watching the multiverse evolve, but it suffers from a severe problem. Because the inflating regions expand exponentially while pocket universes form at a constant rate per unit volume, the vast majority of observers at any proper time cutoff exist in the youngest pocket universes, those that nucleated most recently. This leads to predictions that conflict with observation, suggesting we should expect to find ourselves in a universe that just barely permits our existence. The scale factor cutoff measure instead counts observers that form before the scale factor of the inflating background reaches a specified value. This modification changes the weighting dramatically because it accounts for the exponential expansion of inflating regions. Under this measure, older pocket universes contribute more observers simply because they have had more time to develop complex structures. The scale factor cutoff produces predictions more consistent with our observations, including reasonable values for the cosmological constant, But the choice of scale factor rather than proper time lacks clear physical justification. A more sophisticated approach, the causal patch measure, restricts attention to the region of spacetime causally accessible to a single observer. In an eternally inflating universe with positive cosmological constant, each observer's causal patch has finite 4-volume, approximately 10 to the power of 124 Planck volumes for our observed vacuum energy. This finite volume contains only finitely many observers, potentially avoiding the infinity over infinity problem. The causal patch measure predicts that typical observers should find themselves in universes where the cosmological constant is small enough to permit structure formation, but not much smaller, matching our observations reasonably well. Yet another proposal, the stationary measure, exploits the time translation symmetry of eternal inflation in its asymptotic future. After sufficient time, the statistical properties of the multiverse approach a steady state where the rate of pocket universe formation balances the exponential expansion of inflating regions. This equilibrium distribution provides a natural weighting without arbitrary cutoffs. The stationary measure yields predictions similar to the causal patch measure for many observable quantities, suggesting some underlying connection between these apparently different approaches. The fat geodesic measure attempts to sample the multiverse by following the world line of a small comoving volume through the inflating background. This geodesic occasionally enters pocket universes, spending time, proportional to their proper volume, before the cosmological constant drives exponential expansion. The resulting distribution over observations depends on the detailed geometry of vacuum transitions and the dynamics of structure formation within each pocket type. Each measure makes different predictions for the probability distribution of physical constants, the likelihood of various cosmological histories, and the expected properties of typical observers. Some measures predict that most observers should find themselves in large, old, nearly empty universes. Others suggest that typical observers inhabit young, dense regions shortly after their pocket universe nucleated. The disagreement between measures extends to fundamental questions about the nature of time, causality, and observation in an infinite multiverse. The youngness paradox illustrates the severity of these disagreements. Under certain measures, the exponential expansion of inflating regions implies that most observers exist in pocket universes that formed as recently as possible, consistent with the development of complexity. This would suggest that we should expect our universe to be much younger than its apparent 13.8 billion years, with structure formation occurring through improbable statistical fluctuations rather than gradual gravitational collapse. The fact that we observe an old universe with structure formed through conventional astrophysical processes either rules out these measures or indicates that we are highly atypical observers. The Boltzmann brain problem connects directly to the measure problem through questions about the relative abundance of different observer types. If a measure weights late-time observations heavily, the vast stretches of de Sitter space in our universe's future contribute enormous numbers of potential Boltzmann brain fluctuations. These random observers would vastly outnumber evolved beings like ourselves, making our existence as biological organisms statistically miraculous. Avoiding this conclusion requires either a measure that suppresses late-time contributions or a physical mechanism that prevents the long-term persistence of our vacuum state. Some physicists argue that the measure problem indicates a fundamental incompleteness in our understanding of quantum mechanics and cosmology. Perhaps the correct theory will provide a unique, physically motivated measure that resolves all ambiguities. Others suggest that the measure problem reveals the limits of scientific inquiry, that questions about typical observers in an infinite multiverse may simply lack meaningful answers. The absence of a principled solution after decades of investigation has led some researchers to question whether eternal inflation, despite its theoretical elegance, can ever yield testable predictions. The mathematical structure of the measure problem connects to deep questions in probability theory and the philosophy of infinity. When dealing with infinite sets, the concept of proportion becomes problematic. The even integers and the odd integers are both infinite, yet we intuitively want to say each comprises half of all integers. Formalizing this intuition requires careful limiting procedures that do not always yield unique answers. The multiverse measure problem represents a physical manifestation of these mathematical subtleties, complicated further by the dynamical nature of eternal inflation and the observer-dependent character of probability. Information-theoretic approaches offer potential new perspectives on the measure problem. Perhaps the correct measure emerges from considering the algorithmic complexity of different observations, weighting simpler patterns more heavily than complex ones. This connects to the mathematical universe hypothesis, where the measure on mathematical structures might derive from their descriptive complexity. Simpler structures, requiring shorter specifications, would dominate the ensemble of all possible realities. The resolution of the measure problem, if one exists, will likely reshape our understanding of probability, observation, and existence in fundamental ways. The question of what we should expect to observe, given that we exist as conscious beings, touches on the deepest issues in physics and philosophy. Until this puzzle finds resolution, the predictive power of eternal inflation remains limited, suspended between mathematical elegance and empirical testability, between the infinite possibilities of the multiverse and the finite observations available to any single observer, embedded within its vast expanse. The tension between mathematical elegance and empirical testability strikes at the heart of what distinguishes science from other forms of knowledge. Karl Popper, the philosopher who shaped 20th century understanding of scientific methodology, proposed falsifiability as the demarcation criterion separating scientific theories from metaphysical speculation. A theory qualifies as scientific in this framework only if it makes predictions that could, in principle, be shown false by observation. The multiverse hypothesis, with its infinite array of unobservable domains, seems to challenge this criterion in fundamental ways. The concern runs deeper than mere practical inaccessibility. Many accepted scientific theories describe phenomena beyond direct observation. Quarks remain forever confined within hadrons, never appearing as isolated particles. Yet the standard model of particle physics makes precise predictions about scattering experiments that confirm their existence indirectly. The interior of the Sun lies beyond any probe we could send, Yet helioseismology and neutrino detection reveal its structure with remarkable precision. Black hole interiors hide behind event horizons, causally disconnected from external observers, yet general relativity's predictions about their external effects have been spectacularly confirmed by gravitational wave detections from LIGO and Virgo, measuring space-time ripples from mergers billions of light-years distant. The multiverse presents a different challenge. Other bubble universes in eternal inflation lie not merely beyond current technology, but beyond any possible observation, separated by inflating space that expands faster than light can traverse. The causal structure of space-time itself forbids information exchange between these domains. No signal, no particle, no gravitational wave could ever reach us from a universe nucleated in a different vacuum state of the string landscape. The separation is not practical, but fundamental, built into the geometry of eternal inflation at the deepest level. Yet proponents of multiverse theories argue that falsifiability applies to theoretical frameworks, not to every entity those frameworks describe. Inflation as a theory makes testable predictions about our observable universe, predictions that have been confirmed with increasing precision. The cosmic microwave background exhibits the nearly scale-invariant spectrum of primordial fluctuations that inflation predicts, with a spectral index measured at approximately 0.965 by the Planck satellite, matching inflationary calculations. The spatial flatness of the universe, with curvature constrained to less than 0.4% deviation from perfect flatness, confirms another inflationary prediction. The absence of magnetic monopoles and other topological defects expected from grand unified phase transitions finds natural explanation in inflationary dilution. If inflation explains these observations, and if the same theoretical framework that produces inflation also produces eternal inflation as a generic consequence, then the multiverse emerges not as an arbitrary addition, but as an unavoidable implication of our best-tested cosmological theory. The logic resembles accepting the existence of regions beyond our cosmic horizon. We cannot observe galaxies more than 46 billion light-years distant, the current radius of the observable universe, yet we have no reason to suppose the universe ends at this boundary. The same physics that operates within our horizon presumably continues beyond it. Similarly, the same inflationary dynamics that shaped our observable patch presumably continues in regions we cannot see, eternally spawning new bubble universes. String theory faces similar scrutiny regarding its scientific status. The theory's predictions about observable physics depend on which of the estimated 10 to the power of 500 vacuum states describes our universe. Without a selection principle determining this choice, the theory seems to predict everything and therefore nothing. Critics argue this represents a retreat from the predictive ambitions that characterized 20th century physics, when theorists sought unique mathematical structures that would determine all physical constants from first principles. Defenders respond that string theory does make definite predictions, though of a different character than traditional theories. It predicts the existence of gravity, requiring spin-2 massless particles in any consistent string background. It predicts supersymmetry at some energy scale, though that scale might lie far above current accelerator capabilities. It predicts extraspatial dimensions, though these might be compactified at the Planck length of 1.6 times 10 to the minus 35 meters, forever beyond direct detection. It predicts specific relationships between coupling constants and compactification geometry that could, in principle, be tested if we knew the correct vacuum state. The anthropic reasoning that accompanies multiverse theories introduces another layer of complexity to the falsifiability question. If physical constants vary across the multiverse, and if observers can only exist in regions where constants permit complex chemistry and stable structures, then we should expect to find ourselves in an atypical region, one fine-tuned for life. This reasoning successfully predicted the approximate value of the cosmological constant before its measurement. Steven Weinberg calculated in 1987 that the cosmological constant must be small enough to permit galaxy formation, yielding an upper bound within 1 or 2 orders of magnitude of the value eventually measured at approximately 10 to the minus 123 in Planck units. This successful prediction demonstrates that anthropic reasoning within a multiverse framework can yield testable consequences. The prediction was not that the cosmological constant would take any particular value, but that it would fall within a range compatible with our existence. The actual measured value, while small by particle physics standards, is not unnaturally small given the anthropic constraint. Had the cosmological constant been measured at exactly 0, or at a value thousands of times smaller than the anthropic bound, the multiverse explanation would have faced serious difficulty. Yet critics note the asymmetry in how such reasoning is applied. A successful anthropic prediction is claimed as evidence for the multiverse, while a failed prediction might be explained away by invoking unknown selection effects or additional constraints. The flexibility of anthropic reasoning, its ability to accommodate a wide range of outcomes, limits its power to discriminate between theories. A truly predictive framework should risk falsification, should make sharp predictions that could clearly fail. The debate connects to deeper questions about the goals of physics. Is the purpose of physical theory to predict observations or to explain the underlying reality that produces those observations? Instrumentalists argue that theories are merely tools for organizing experience, successful to the extent they predict experimental outcomes. Realists counter that physics aims at truth about the world, that successful predictions indicate theories have captured something real about nature's structure. The multiverse challenges both perspectives, offering a framework that might be true yet largely untestable, or that makes statistical predictions without determining specific outcomes. Some physicists propose that the multiverse should be evaluated not by traditional falsifiability, but by broader criteria of theoretical virtue. Does it solve problems that otherwise lack solutions? Does it emerge naturally from well-motivated theoretical frameworks? Does it cohere with other successful theories? Does it suggest new research directions that prove fruitful? By these measures, the multiverse scores reasonably well. It addresses the fine-tuning problem without invoking design. It emerges from inflationary cosmology and string theory, both developed for independent reasons. It connects quantum mechanics, cosmology, and particle physics in a unified framework. The comparison with other scientific revolutions proves instructive. When Copernicus proposed heliocentrism, the theory initially made worse predictions than the Ptolemaic system it sought to replace. Its virtues were aesthetic and philosophical, removing Earth from the cosmic center and simplifying planetary motions. Only later did improved observations and Kepler's elliptical orbits demonstrate heliocentrism's empirical superiority. Similarly, the multiverse might represent a framework whose full empirical consequences remain to be discovered, whose testable predictions await theoretical developments we cannot yet anticipate. Potential observational signatures do exist, though they remain speculative and challenging to detect. Bubble collisions in eternal inflation could leave imprints on the cosmic microwave background, circular patterns of temperature variation where our bubble universe encountered another during its early expansion. Searches for such signatures in Planck satellite data have found no convincing evidence, constraining but not ruling out certain collision scenarios. The absence of detection might indicate that collisions are rare, that their signatures are too faint, or that eternal inflation does not occur. Gravitational wave astronomy opens another window. The stochastic background of gravitational waves from the early universe carries information about inflationary dynamics. Future detectors like LISA, planned for launch in the 2030s, might detect primordial gravitational waves with frequencies around 10 to the minus 3 Hz, probing energy scales approaching 10 to the 16 giga-electron volts where inflation likely occurred. Deviations from simple inflationary predictions could hint at more complex dynamics, perhaps reflecting the landscape structure of string theory or the bubble nucleation processes of eternal inflation. The scientific status of the multiverse thus remains genuinely uncertain, suspended between established physics and untestable speculation. It emerges from our best theories, yet resists direct confirmation. It solves deep puzzles, yet introduces new ones. It extends the scientific worldview to cosmic scales, yet challenges the methodology that built that worldview. The resolution of this tension will shape the future of fundamental physics, determining whether the multiverse joins the pantheon of accepted scientific concepts or remains forever in the borderland between physics and philosophy, mathematically compelling yet empirically elusive. The cosmic microwave background offers perhaps the most promising window into physics beyond our observable horizon, a fossil record of the universe's earliest moments that might contain subtle imprints of processes occurring in regions we can never directly observe. This ancient light, released approximately 380,000 years after the Big Bang, when the universe cooled to roughly 3,000 Kelvin and electrons, first combined with protons to form neutral hydrogen, carries information about conditions in the primordial plasma with extraordinary fidelity. The photons that compose this radiation have traveled for 13.8 billion years, their wavelengths stretched by cosmic expansion from visible light to microwaves, with a peak wavelength of about 1.9 millimeters, corresponding to a temperature of 2.725 Kelvin above absolute zero. The uniformity of this radiation across the sky provides powerful evidence for cosmic inflation, the brief period of exponential expansion that stretched microscopic quantum fluctuations to astronomical scales. Before inflation, regions that now appear on opposite sides of our sky were close enough to reach thermal equilibrium, explaining why the microwave background temperature varies by only about 1 part in 100,000 across the entire celestial sphere. These tiny temperature variations, measured with exquisite precision by satellites including COBE, WMAP, and Planck, encode information about the density fluctuations that would eventually grow under gravitational attraction to form galaxies, clusters, and the vast cosmic web of structure we observe today. The statistical properties of these fluctuations match the predictions of inflationary theory with remarkable accuracy. The power spectrum, which describes how the amplitude of temperature variations depends on their angular scale, follows a nearly scale-invariant pattern with a spectral index of approximately 0.965, slightly less than unity as inflation predicts. The fluctuations appear Gaussian to high precision, meaning their statistical distribution follows the bell curve expected from quantum vacuum fluctuations amplified by exponential expansion. The phases of different Fourier modes appear random and uncorrelated, consistent with their origin in independent quantum events during the inflationary epoch. Yet within this framework of successful predictions lies the possibility of detecting signatures from beyond our cosmic horizon. If eternal inflation produces a vast ensemble of bubble universes, and if our own universe nucleated as one such bubble, then collisions between our bubble and neighboring bubbles could leave observable imprints in the microwave background. The physics of such collisions depends on the relative velocities of the bubbles, the properties of the domain walls separating different vacuum states, and the geometry of the collision surface as it intersects our past light cone. A bubble collision would create a distinctive pattern in the cosmic microwave background, a circular or nearly circular region where the temperature and polarization differ systematically from the surrounding sky. The collision surface, propagating at nearly the speed of light, would sweep through the primordial plasma, potentially altering its temperature, density, or ionization state in ways that persist as the universe expands and cools. The resulting signal would appear as a disc-shaped anomaly, with the temperature deviation following a characteristic profile that depends on the collision parameters. The expected signature involves several components that distinguish it from other sources of cosmic microwave background anisotropy. The temperature deviation within the collision disk would follow a specific radial profile, typically showing a sharp edge at the boundary where the collision surface intersected our observable universe. The amplitude of the deviation depends on the energy released in the collision and the properties of the domain wall, with theoretical estimates ranging from undetectably small to potentially observable levels of order 10 to 100 microkelvin. The polarization pattern would show distinctive features, with the electric mode polarization exhibiting azimuthal symmetry around the collision center and potentially generating magnetic mode polarization through secondary effects. Several research groups have searched the Planck satellite data for evidence of bubble collision signatures, developing sophisticated statistical techniques to identify circular anomalies that match the predicted profiles. The analysis requires careful treatment of foreground contamination from our own galaxy, instrumental noise, and the cosmic variance that limits our ability to distinguish genuine signals from statistical fluctuations in a single realization of the primordial perturbations. The searchers have identified candidate regions that warrant further investigation, though none has achieved the statistical significance required to claim detection. The most intriguing candidates appear as cold spots or temperature decrements in specific directions, with angular sizes ranging from a few degrees to tens of degrees on the sky. The famous cold spot in the constellation Eridanus, a region approximately 10 degrees across, where the microwave background temperature falls about 70 microkelvin below the average, has attracted particular attention as a possible collision signature. However, alternative explanations exist, including the integrated Sachs-Wolf effect from a supervoid along the line of sight, and the statistical significance of the anomaly remains debated. The theoretical predictions for bubble collision signatures depend sensitively on parameters that remain poorly constrained. The nucleation rate of bubbles in the eternally inflating background determines how many collisions might have occurred within our past light cone, with estimates varying over many orders of magnitude depending on the shape of the potential energy landscape. The properties of the domain walls separating different vacuum states determine the energy released in collisions and the resulting temperature perturbations. The geometry of eternal inflation, including whether our bubble formed early or late in the process, affects the expected number and angular size distribution of collision signatures. String theory's landscape of vacuum states provides a concrete framework for estimating these parameters, though the calculations involve significant uncertainties. The landscape contains perhaps 10 to the power 500 distinct vacuum configurations, each corresponding to a different way of compactifying the extra dimensions and stabilizing the moduli fields that determine low-energy physics. Transitions between these vacua occur through quantum tunneling, with rates that depend exponentially on the height and width of the potential barriers separating them. The resulting bubble nucleation rates vary enormously across the landscape, making precise predictions difficult without better understanding of the measure problem discussed earlier. Beyond bubble collisions, the cosmic microwave background might contain other signatures of multiverse physics. If our universe underwent a phase transition during or after inflation, domain walls separating regions with different vacuum properties could generate distinctive patterns in the temperature and polarization maps. Cosmic strings, one-dimensional topological defects predicted by many extensions of the standard model, would create line-like discontinuities in the microwave background through the Kaiser-Stebbins effect, where photons passing on opposite sides of a moving string experience different gravitational redshifts. The polarization of the cosmic microwave background offers additional channels for detecting exotic physics. The magnetic mode or B-mode polarization pattern, generated by gravitational waves or by gravitational lensing of the electric mode pattern, carries information about tensor perturbations from inflation and about the matter distribution along the line of sight. Primordial gravitational waves with amplitudes detectable by current or planned experiments would indicate inflation occurred at energy scales near 10 to the power 16 gigaelectron volts. close to the grand unification scale where the strong and electro-weak forces might merge. The amplitude of these waves, characterized by the tensor-to-scalar ratio, remains an active target of observational searches, with current upper limits around 0.03 from combined Planck and BICEP/Keck data. The search for multiverse signatures in the cosmic microwave background exemplifies the broader challenge of testing theories that make predictions about regions beyond our observational horizon. The signatures, if they exist, would appear as subtle statistical anomalies in data dominated by the well-understood physics of the primordial plasma and its subsequent evolution. Distinguishing genuine signals from instrumental artifacts, foreground contamination, and chance fluctuations requires sophisticated analysis techniques and independent confirmation from multiple experiments. Future observations will significantly improve our sensitivity to these exotic signatures. Ground-based experiments, including the Simons Observatory and CMB-S4, will map the microwave background polarization with unprecedented precision, potentially detecting or constraining primordial gravitational waves at the level of tensor-to-scalar ratios below 0.001. Space-based concepts under development would extend these measurements to larger angular scales inaccessible from the ground, where bubble collision signatures might be most prominent. The combination of improved sensitivity, broader frequency coverage, and better understanding of systematic effects will either reveal evidence for physics beyond our horizon or place increasingly stringent limits on the observable consequences of multiverse scenarios. The observable universe extends outward from every point in space, a sphere defined not by any physical boundary, but by the finite speed of light and the finite age of cosmic expansion. Light that departed from distant sources more than 13.8 billion years ago is only now reaching our telescopes, having traveled across the expanding fabric of space-time to deliver information about conditions in the early universe. The commoving distance to this cosmic horizon measures approximately 46.5 billion light-years, a number larger than the age of the universe multiplied by the speed of light, because space itself has stretched during the photon's journey. Beyond this horizon lies a realm forever hidden from direct observation, a domain where events unfold that can never influence our measurements or be influenced by our actions. The particle horizon represents the maximum distance from which light could have reached us since the beginning of time, while the event horizon marks the boundary beyond which light emitted today will never reach us in the infinite future. These two horizons differ because the accelerating expansion driven by dark energy continuously pushes distant regions beyond our causal reach. Galaxies currently visible at the edge of our observable universe are already receding faster than light due to the expansion of intervening space, their images frozen in time as they approach the event horizon. The Hubble parameter, currently measured at approximately 67.4 kilometers per second per megaparsec, quantifies this expansion rate, meaning that for every megaparsec of distance, the recession velocity increases by this amount until eventually exceeding the speed of light at sufficiently large separations. The cosmic microwave background radiation originates from the surface of last scattering, a spherical shell located at a moving distance of about 45.4 billion light-years, where the universe first became transparent approximately 380,000 years after the initial expansion began. This radiation has been stretched by a factor of roughly 1,100 due to cosmic expansion, shifting from the roughly 3,000 Kelvin thermal glow of the primordial plasma to the 2.725 Kelvin microwave background we observe today. The temperature fluctuations imprinted on this radiation, measuring approximately 1 part in 100,000, encode information about density variations in the early universe that eventually grew into the galaxies and galaxy clusters we observe in the present epoch. Beyond the surface of last scattering lies a realm of even earlier cosmic history, accessible only through different messengers. Gravitational waves generated during inflation would have propagated freely through the opaque plasma that blocked electromagnetic radiation, potentially carrying information about the universe's first fraction of a second. The cosmic neutrino background, predicted to have decoupled when the universe was approximately 1 second old and the temperature exceeded 10 billion Kelvin, represents another fossil record from before the electromagnetic horizon. These neutrinos, now cooled to approximately 1.95 Kelvin, pervade all of space at a density of roughly 336 neutrinos per cubic centimeter, though their extremely weak interactions make direct detection extraordinarily challenging. The inflationary paradigm suggests that our observable universe represents an infinitesimally small fraction of the total volume generated during the exponential expansion phase. If inflation lasted for even 60 e-foldings, the minimum required to solve the horizon and flatness problems, the total inflated volume would exceed our observable universe by a factor of at least 10 to the power of 78. The eternal inflation scenario extends this picture dramatically, proposing that inflation continues indefinitely in most of space, with our observable universe occupying a single bubble that nucleated when the inflaton field decayed to a lower energy state. The total volume of eternally inflating space grows without bound, continuously spawning new bubble universes at a rate that outpaces any finite counting. The geometry of space within our observable universe appears extraordinarily flat, with measurements from the cosmic microwave background constraining the curvature parameter to within 0.4% of zero. This flatness emerges naturally from inflation, which stretched any initial curvature to undetectable levels, much as the surface of a balloon appears flat when examined on scales much smaller than its radius. The total density of the universe, including matter, radiation, and dark energy, equals the critical density of approximately 9.47 times 10 to the negative 27 kilograms per cubic meter to remarkable precision. This critical density represents the exact balance between gravitational attraction and the kinetic energy of expansion, a balance that inflation automatically establishes regardless of initial conditions. The accelerating expansion driven by dark energy, which constitutes approximately 68% of the total energy density, fundamentally limits our future observational capabilities. As the universe ages, the event horizon shrinks in moving coordinates, meaning that fewer and fewer distant objects remain within our causal future. In approximately 150 billion years, the only galaxies remaining within our observable universe will be those currently gravitationally bound within the local group, a collection of roughly 80 galaxies spanning about 10 million light-years. The rest of the cosmic web will have receded beyond the event horizon, their light red-shifted to undetectable wavelengths, leaving future observers in an apparently isolated island universe with no evidence of the vast cosmic structure that currently surrounds us. The relationship between our finite observable horizon and the potentially infinite extent of space beyond raises profound questions about the nature of physical reality. If space extends infinitely and the laws of physics remain uniform, then statistical arguments suggest that every possible configuration of matter must be realized somewhere, simply because an infinite volume contains infinitely many opportunities for any finite arrangement to occur. The distance to an exact copy of our observable universe, assuming random initial conditions, has been estimated at approximately 10 to the power of 10 to the power of 118 meters, a number so vast that it dwarfs any meaningful comparison, yet remains finite within an infinite space. This statistical inevitability of repetition across infinite space connects directly to the fundamental laws governing the flow of energy and the accumulation of disorder, the thermodynamic principles that ultimately determine the fate of every structure in every possible universe. The second law of thermodynamics, formulated in the 19th century by Rudolf Clausius and Ludwig Boltzmann, describes the inexorable tendency of closed systems to evolve toward states of maximum entropy, toward configurations where energy spreads as uniformly as possible, and the capacity to perform useful work diminishes toward zero. Entropy, measured in units of joules per Kelvin, quantifies the number of microscopic arrangements consistent with a given macroscopic state. A cup of hot coffee in a cold room represents a low entropy configuration because relatively few molecular arrangements produce that specific temperature gradient. As heat flows from the coffee into the surrounding air, the system evolves toward the vastly more probable state, where both coffee and room share the same temperature, a configuration compatible with an astronomically larger number of microscopic possibilities. Boltzmann's famous equation, S equals K times the natural logarithm of W, relates the entropy S to the number of microstates W through the Boltzmann constant K, approximately 1.38 times 10 to the negative 23 joules per Kelvin. The universe as a whole appears to obey this same thermodynamic logic on the grandest scales. The cosmic microwave background radiation, with its temperature of 2.725 Kelvin, represents a nearly uniform thermal bath that fills all of space, the cooled remnant of the hot, dense state that existed 13.8 billion years ago. As the universe continues to expand, this radiation will cool further, asymptotically approaching absolute zero over timescales measured in trillions of years. Stars will exhaust their nuclear fuel, galaxies will fade into darkness, and the matter that once formed planets and people will disperse into an ever more dilute cosmic void. The timescales involved in this cosmic dissolution stretch far beyond ordinary comprehension. The last stars, Red dwarfs burning their hydrogen fuel with miserly efficiency will flicker out approximately 100 trillion years from now, some 10,000 times the current age of the universe. After this stellar era ends, the universe enters a degenerate era dominated by the cooling remnants of dead stars, white dwarfs and neutron stars and black holes drifting through an expanding darkness. White dwarfs will gradually crystallize and cool over perhaps 10 to the power of 17 years, their temperatures dropping toward the ambient cosmic background. Black holes, those gravitational endpoints where matter collapses beyond the event horizon, might seem like permanent features of the cosmic landscape, but even they cannot escape the reach of thermodynamics. Stephen Hawking's theoretical work in 1974 revealed that black holes emit thermal radiation through a quantum mechanical process involving virtual particle pairs near the event horizon. This Hawking radiation carries energy away from the black hole, causing it to slowly evaporate over immense timescales. A black hole with the mass of the Sun would require approximately 10 to the power of 67 years to evaporate completely, while the supermassive black holes at galactic centers containing billions of solar masses would persist for perhaps 10 to the power of 100 years before finally dissolving into radiation. The temperature of Hawking radiation depends inversely on the black hole's mass, following the formula T equals h bar times c cubed divided by 8p times g times m times the Boltzmann constant, where h bar represents the reduced Planck constant, c the speed of light, g the gravitational constant, and m the black hole mass. A solar mass black hole radiates at approximately 60 nanokelvins, far colder than the current cosmic microwave background, which means such black holes actually absorb more energy from their surroundings than they emit. Only after the universe cools below this threshold will stellar mass black holes begin their slow evaporation. Information theory developed by Claude Shannon in 1948 provides another lens through which to view the fate of physical systems. Shannon defined information entropy in terms of probability distributions, quantifying the uncertainty or surprise associated with messages and signals. The mathematical parallels between Shannon entropy and Boltzmann's thermodynamic entropy run deep, reflecting a fundamental connection between physical disorder and informational uncertainty. The Bekenstein bound, proposed by Jacob Bekenstein in 1981, establishes a maximum limit on the information that can be contained within a given region of space, proportional to the area of the bounding surface rather than its volume. For a sphere of radius r containing energy E, this bound equals 2 pi times r times E divided by h bar times c times the natural logarithm of 2, measured in bits. Black holes saturate this bound, containing the maximum possible information for their size, with their entropy proportional to the area of their event horizon, measured in Planck units. The Planck area, approximately 2.6 times 10 to the negative 70 square meters, represents the quantum of area, and a black hole's entropy equals 1/4 of its horizon area, divided by this fundamental unit. A solar mass black hole thus contains approximately 10 to the power of 77 bits of information, an almost inconceivable quantity encoded in the quantum structure of the horizon. The holographic principle, emerging from the work of Gerard 't Hooft and Leonard Susskind in the 1990s, generalizes this observation to suggest that all the information within any region of space can be encoded on its boundary. This principle implies a profound reduction in the true degrees of freedom of physical systems, suggesting that the three-dimensional world we perceive may be a projection of information stored on distant two-dimensional surfaces. In the context of eternal inflation, each bubble universe might be described by information encoded on its boundary, a holographic screen separating one vacuum state from another. As the universe approaches its final state, the concept of thermal equilibrium takes on cosmic significance. The heat death scenario, first articulated by Lord Kelvin in the 19th century, envisions a universe where all temperature gradients have smoothed out. All energy has degraded to its lowest useful form, and no further work or computation can occur. This state of maximum entropy represents the thermodynamic endpoint of cosmic evolution, a condition of perfect uniformity and absolute stillness that persists forever. Yet the quantum nature of space-time may prevent true equilibrium from ever being achieved. Vacuum fluctuations, those momentary borrowings of energy permitted by the uncertainty principle, continue even in empty space at zero temperature. The energy-time uncertainty relation, delta E times delta T, greater than or equal to h bar over 2, allows virtual particles to briefly exist before annihilating, creating a subtle quantum foam that never quite settles into perfect stillness. These fluctuations, though individually insignificant, accumulate over the vast time scales of the far future, occasionally producing larger statistical deviations that might seed new structures or even new inflationary episodes. The fate of information itself remains one of the deepest puzzles in theoretical physics. When matter falls into a black hole, and the black hole subsequently evaporates through Hawking radiation, what happens to the information that described the original matter? Hawking initially argued that this information was lost, violating the unitarity of quantum mechanics, but subsequent work suggests that information may be preserved in subtle correlations within the Hawking radiation. The resolution of this black hole information paradox may require a complete theory of quantum gravity, a framework that unifies general relativity with quantum mechanics at the Planck scale. Across the multiverse, if eternal inflation produces an infinite ensemble of bubble universes, each pocket cosmos traces its own thermodynamic trajectory toward equilibrium. Some bubbles may contain physical constants that permit long-lived structures and complex chemistry, while others may expand too rapidly for matter to clump, or may recollapse before any interesting structures form. The distribution of outcomes across this vast ensemble depends on the landscape of vacuum states and the dynamics of bubble nucleation, with each universe representing one realization of the underlying physical possibilities. The ultimate fate of all these realities converges towards the same thermodynamic endpoint, a state of maximum entropy where the distinction between different histories becomes meaningless. Information disperses, structures dissolve, and the arrow of time itself loses its meaning in a universe where nothing changes and no observer remains to mark the passage of moments. This cosmic stillness, extending across infinite space and eternal time, represents the final chapter in the story of physical reality, a quiet conclusion written in the language of thermodynamics and probability, where the vast complexity of stars and galaxies and minds ultimately returns to the simple uniformity from which it emerged.